Uno, check, check. Dos, check. Check.
test. Huh? Okay, hello everyone. Welcome to the Danksharding workshop, Devcon edition. And cool. So first, I guess half of you have already know what is Danksharding. Oops. Okay, and so this is the latest Ethereum. One moment. It's the surge. um, cool. Let's continue. So it's the latest Ethereum sharding design that proposed by Danksharding. He's here today in 2021, and so in this new design that it unlocked so many scaling. I mean the challenge, and it's not now the sharded data. We shard it at the data blobs rather than having many EVM shard chains. But the Danksharding protocol is there are still some technical challenge that we need to fix. So right before we have the full Danksharding, Proto is also here, and many of us they collaborated and figure out that we can have a more feasible solutions that in the short term to address this scalings, and it can greatly scale the Ethereum with their two rollups in the very near future. So that's the Proto and Danksharding, and it's the Proto Danksharding sharding. Okay, so there are some many common features in both EIP 4.4 and the full Danksharding. So today we will break down these topics, and you can see that they both have the KZG commitment. So Danksharding will introduce the cryptography part first, and they also have the Blob transactions. So we will also introduce like what is Blob today. And fee market is also the shared common features here. And so the challenging part of Danksharding is the PBS and the DAS. So we will also talk about it later. Okay. Is the agenda today. We have a very rich agenda in the next 2 hours. So yeah, and I will hand it to Danksharding next to introduce the cryptography in Danksharding. So if you can go through this, you will know everything. Okay, that's the click.
Thank you, Xiaowen. Cool. So I will be giving an introduction to KZG commitments. I'll be starting with giving a motivation to understand why we need these advanced polynomial commitments and why we can't do all this simply with Merkle roots, which we're all quite familiar with. So I'll be going through the motivation. I'll quickly go give an overview over the finite fields that we use in order to commit to polynomials. I will kind of motivate KZG commitments as like hashes of polynomials. Then go to the actual meat, which is how do KZG commitments work. And finally, because we also use these a lot in our construction now, I will be going through the technique which I call random evaluation, which is a nice trick that you can often use to work with polynomials, and that makes a lot of things that you want to do with polynomials a lot more efficient. Cool. So let's talk about data availability sampling and erasure coding. So what's data availability sampling? So the idea is we somehow have a large blob of data, and what we're working on is scalability. So scalability means that somehow we have to make it so that a node has to do less work to achieve the same thing that we do today. So right now, every node ensures that all Ethereum blocks are available by downloading all the blocks. That's just an implicit part of it. Like, it seems obvious because right now you also execute the full blocks, but it's one of the things that don't scale in the current Ethereum system. So we need a way to reduce this workload, but we want to do it in such a way that we don't lose any of the security that this provides, and that's what makes this tricky. And so like the basic idea is, okay, what if we take our data blob and we just check that random samples of the data are available. So if we do this naively, if we just take the data as it is, then this does not really work, because even missing a tiny amount of data is catastrophic potentially for a blockchain. But by doing random sampling, you can never find out whether a tiny bit is missing. You can only see whether major parts of the data are missing. So what we'll need to do is, in order for this technique to work, is we need to encode the data in such a way that that even having some parts of the data, say 50%, is enough to guarantee that all the data is available. And so the way we do this is we extend the data using a so-called Reed-Solomon code. And if you know a little bit about polynomials, like a Reed-Solomon code is nothing else but extending the data using a polynomial. So what you do is, let's say, like in the simple example, we have 4 blocks of original data. And what we'll do is we will take these 4 as evaluations of a polynomial. There will always be a polynomial of degree 3 that goes through these 4 points. And then we can evaluate this polynomial for more points. And what this means, because 4 points always determine a polynomial of degree 3, that any of these 4 points are enough to reconstruct exactly the same polynomial. It does not matter which 4 points you have. And so this is the basis of erasure coding. And now, because of this, the data availability sampling idea that we had here actually works, because now I don't need to ensure that every single bit of the data is available. Now I only need to know that at least 50% of the data are available, and then I can always reconstruct everything. Yeah, sure.
Is it now double the data?
Yes, yeah, we have doubled the data. No. So that's the trick. So we do random sampling. So as an example, we query 30 random blocks. So if the data is not available, that means the attacker needs to have withheld 50%. Because if they submitted more than 50% to the network, it's all there. Okay, so if it's not available, then each of these samples, because we used local randomness to query them, has only a 50% chance of succeeding. So that means in aggregate, the probability that all of them succeed is now 2 to the minus 30, which is 1 in a billion. So this is why it scales. You don't need to query 50% of the data. You only need to do like a tiny number of random samples. And this number is constant, so it does not depend on the amount of data. Okay. So what if we have this polynomial, so we have these evaluations. This was the original data, D0 to D3. And then we have these extensions that we computed. And we just compute a normal Merkle tree on top of that and use this root as our data availability root. So the problem with this is that Merkle roots do not tell you anything about the content of the data. So like it could be anything. So in this case, let's say an attacker wants to trick our data availability system. They could just not use this polynomial extension, but they could just put random data. So basically, in coding terms, they have provided an invalid code. What that means is that if you get 4 different chunks of this data, you would always get a different polynomial. So you would so consensus is all about agreeing on like something, like and in this case we wouldn't actually have agreed on something because the data is different depending on which on which of these samples we've got. So the only way to make this work is if we add fraud proofs to the system, where you basically prove that that someone has provided this invalid code, but that isn't great. So that has some problems. They add a lot of complexity, and particularly in this case, because this is about the layer 1 itself, it would make our system very, very difficult to design, because now validators would need to basically wait for this fraud proof in order to know which block to even vote for. So it would be kind of very iffy to design this. So the interesting question is, what if we could find some kind of commitment that instead always commits to a polynomial? So we always know that the encoding is valid. Cool, and that is why we will introduce KZG commitments. And we need to start a little bit earlier. So I will start by introducing finite fields a little bit for those who are not familiar with it. Okay, sorry, I can do it from here. Okay, so what's a finite field? Okay, so to understand what a field is, it's basically think about rational, real, or complex numbers, which you've already learned about. And just remind yourself, like, we have basic operations that we can do in them. We can add, subtract, multiply, and divide. And we can do all of these except division by 0, so that you're always able to do these operations. And you have some laws, like they're associative, commutative, distributive. Basically, just think of like, I could give like the formal laws here, but I don't think that would be the best illustration, because you're already very familiar with these rules when you work with rational or real numbers. And the big difference for finite fields is that unlike these fields that we're very familiar with, which all have an infinite number of elements, they have a finite number of elements. And that's quite important, because otherwise we can't encode them with a finite number of bits, which is kind of like something that we need to be able to do. So that means that each element can be represented using the same number of bits. And as an example of showing how this works, here's a very small finite field. This is F5, and basically the way it works is you take the 5 numbers 0, 1, 2, 3, 4, and you use your normal integer operations to compute like the addition, subtraction, and multiplication. But whenever you've done that, you take the result and take the remainder after division by 5. So you take it modulo 5. And then when you write it out, basically you'll find that for each element, so we haven't yet defined like how do we do division. So if you write down the multiplication table, you'll find that each element has actually an inverse. So basically, if you take, for example, here like 2, then you can see that 2 times 3 is 6, but modulo 5, that's 1. So it has an inverse. Okay, that's nice. And like then the other way around, 3, the inverse is 2. And for 4, if you take 4 times 4, it's 16. And it's and that's again modulo 5, that's 1. And so we've just found, like, by just listing these numbers, that every element has an inverse. And the reason for that is that 5 is a prime number. So whenever we take these modulo operations, modulo a prime number, then we'll find that we actually have a finite field. And so that's our finite fields. Except that the fields we're going to be working with in practice will have a lot more elements. So the prime that we're going to be using will have 255 bits. So it's like a very, very big number, because we want to be able to represent a lot of numbers in this field. Cool. Okay, so let's think about hashing polynomials. Okay, so a quick reminder, what's a polynomial? So a polynomial is an expression of this form. So it's like a sum over some coefficients, fi, and terms of the times term of the form x to the power of I. So the property is that it has to be finite sum, so it is a sum from 0 to n. N is the degree of the polynomial, and basically the other important thing that you have to always remind yourself, there can never be any negative terms. So you cannot have x to the -1. It's only terms of the form x to the power of 0, 1, 2, 3, and so on. Yeah, and each polynomial defines a polynomial function. So it's important to distinguish between the two. So polynomial is just an expression of this type. So it's just, you could think of it even as a list of coefficients. And then it defines a function. But like, for example, in some fields, like in finite fields, you will have the property that the same polynomial function can have many polynomials corresponding to it, because there's only a finite number of functions, but there's an infinite number of polynomials. This property you don't have in infinite fields. And so the cool property that polynomials have is that for any k points, there will always be a polynomial of degree k minus 1 or lower that goes through all of these points. And this polynomial is unique. And the other property is that a polynomial of degree n that is not constant has at most n zeros. Okay. So what would be cool if we could imagine a hash function for polynomials? So let's imagine that we could have a hash function that takes a polynomial and hashes it. Okay, that's easy. But it should have an extra property, which is that we can construct proofs of evaluation. So basically what we want is that for any z, so any point, we can evaluate those polynomials, compute y equals f of z, and we want some proof that this is correct. So that would be an interesting hash of polynomials that gives us something new. And this hash and the proof should be small in some sense. So here's some idea. Okay, what if we just choose a random number? For example, let's say we choose the number 3. If we want to hash a polynomial, we just evaluate it at this random number, 3. So we put x equals 3. Here's a couple of examples how that works if we stay in our small field f5, which we defined before with just those 5 numbers. So if our polynomial is x squared plus 2x plus 4, then the hash is like x squared 9 plus 2x 6 plus 4 modulo 5 is 4. And then here's a second example, so a bit of a bigger polynomial, modulo 5, in this case it's 0. Okay. That seems a bit stupid to just do it at one point. But the interesting thing is, if our modulus has 256 bits, which is what we're going to work with in practice, it's actually extremely unlikely that 2 randomly chosen polynomials have the same hash in quotation marks, just like it is for a normal hash function, right? So that's an interesting property. Like, I mean, it seems like a very stupid and simple operation, but in some ways, in one way, it already has like a property like a hash. Okay. Okay, so if we accept this for now, then let's have a look at some of the things we could do with it. So for example, we can actually add 2 hashes of polynomials. So like if we have the hash of if we take up the hash of 2 functions, hash of f and f hash of g, then the hash will just be the sum, like the hash of the sum of the functions will just be the hash of f and plus the hash of g. And that's because of this homomorphic property, which is trivial if you write it out in polynomials. The same is true if you multiply two of these polynomial hashes. And that's just because polynomial evaluation itself is a homomorphic property. Like if you can either first add two polynomials, then evaluate them, or you can like evaluate them and then add the result. And the same for multiplication. So it has some really cool properties if we could use this as a hash function. But there's one problem. If you use this, then if someone knows this random number, right, then they could easily create a collision of this polynomial hash function. Because while for random polynomials it's very unlikely that they evaluate to the same point, it is very easy to create like manually two polynomials that evaluate to the same value at this random number. So it doesn't quite work as a hash function as we know it. But what it would be different if somehow instead we could put this random number into a black box. So if we could find a way of computing with these finite field elements, but instead of giving everyone who wants to evaluate this hash function, giving them the actual number, you give them a black box. So like we assume we have a cryptographic way of putting a number into a black box. Then we give them our random number s, and we give them also like the random number s squared and s to the power of 3, but all of them only in the black box. And we do it in such a way, like this black box needs to have the property that you can multiply it with another number, and you can add two of these, but you cannot multiply two numbers in a black box. So if you could do that, then this would actually work, because now the attacker would not be able to like create these two polynomials because they don't know this number, and so they cannot handcraft the polynomials so that they evaluate to the same number at that point. And basically, the cool thing is that elliptic curves actually give you exactly that. So elliptic curves are basically you can think of them as a way of creating black box finite field elements. And the finite field that you have to use is the curve order of that elliptic curve. So if we have an elliptic curve, which we call G1, why we need this index G1 we'll come to later, but it's just elliptic curve that has a generator, which means that that's a point, so that the if you add that point again and again, it will generate your whole curve. And the order of the curve is p, so that's the number of points. And then basically we have the property that that x times g, where x is a finite field element, x times g1, is basically this black box. And the reason for that is that it is hard to compute so-called discrete logarithms. So it's difficult, like when you have computed this x times g1, it is difficult to compute x from that point. So that's a cryptographic assumption. And so if we have that, then if we take if we took two elliptic curve elements, g and h, then we can multiply them with field elements. Like we can compute x times g, we can add the two g plus h, and we can compute linear combinations like x times g plus y times h. But what we can't compute is we can't without computing the discrete logarithm, which is hard, we can't compute something like g times h. And so just like we said before, like we want this black box, so we will introduce the notation like x in squared brackets, 1 for saying that it's in this G1, which is the first elliptic curve we're going to use. We later will need another one. We define that at x times G1. And so basically, when you see these square brackets, think of it as like this is a prime field element in this black box, in this elliptic curve black box. So we can put stuff inside, and there's no easy way to take them back out. But we can do some computations while they're in there. Cool. And with this, we are ready to introduce KZG commitments. Okay. So what we're going to do is we're going to introduce a trusted setup. So we're going to assume that that someone has computed, has taken a random number S, and they've computed inside this box and given to us the powers of S to the power of 0, 1, 2, 3, and so on in our black box. And actually forget this second one for now. We'll come to that later. And so if we take a polynomial function, so we've defined this previously, so it looks like this. It's like a sum of coefficients times powers of x. And we define the KZG commitments as this sum, which we can evaluate. So we take the coefficients and we replace x to the power of I by s to the power of I inside this black box. And here on the left, so this is something we can obviously compute. It's just a linear combination of these elements which we have been given as part of the trusted setup. And the cool thing is, if you write this out, in effect, if it is just f to the power of s evaluated inside this black box. So effectively, we've come back to what we said before. It's just this random evaluation, but we've managed to now randomly evaluate this polynomial inside a black box at the secret point. And yes, and this we call the KZG commitment to the function f. And now, in order to do interesting things with this, we'll need to introduce elliptic curve pairing. So this is where we get our second group. So we actually need a total of two groups. And what we'll have is we have a pairing is a function from two elliptic curve groups and a target group, which is a different kind of group. It's actually not an elliptic curve, but that's not too important here. And it takes basically these two elliptic curve elements, one in G1 and one in G2. And it has the cool property that it is what we call bilinear. And so that what that means is that you can compute this linear combination. So for example, if you have the pairing of a times x and z, then it's basically you can take this a out. The same in the second coefficient. And in addition, if you have the sum, then basically what it does, it splits into these two. So it's like a distributive law here. X plus y times z is e of x, z, and e of y, z. And the same goes again in the second parameter of this function. And basically the cool thing is that this what we couldn't do before inside, yeah. So in the previous slide, target group also knows how to multiply by elements of. Yes. Yeah. And so what we couldn't do previously between elliptic curve points, which is multiply two elliptic curve points, is that we can do in a way between pairings. So if we have one of our points in this first group and one in the second group, then due to this bilinear property, we can it actually in the target group it computes something like x times y, right? So it has this property. We define this additional notation for the target group, and then we have this very clean and nice equation that the pairing of x as a black box element, y as a black box element is x times y. So this is very important, basically. At this point, when we have the pairings, and that's why we really need them, we can do one multiplication. We can only do one because afterwards we get this target group element, and that we can't really do anything with. But it turns out that this is actually enough to do like a lot of very useful stuff in elliptic curves. Okay. Now let's assume that we have two polynomials, f and g. And we commit to those polynomials, but we commit to f in G1 and g in G2 in the different groups. Then basically this pairing actually lets us compute this, like the product of these two commitments, in the target group. So basically, in this really cool polynomial hash that we have defined, we can now if we commit to them in the right groups, we can now multiply two polynomials that are committed in this way. So we can multiply the commitments without even knowing the polynomials themselves. Okay. Cool. Okay, so we will need to introduce one last missing piece in order to fully come to how KZG commitments work and how we can construct proofs, and that is quotients of polynomials. Okay, so let's say we have a polynomial f of x, and we have two field elements y and z. And then we can compute this quotient q of x. This is a rational function, right? So like a polynomial divided by a polynomial is in general a rational function. So you can just see this as like a formal expression. But sometimes this quotient is exact. So sometimes like this quotient will actually result in another polynomial. And basically there's a theorem that's called the factor theorem. It's relatively elementary math. You've probably learned it in school at some point without calling it that. And that basically says that this is a polynomial, this quotient, exactly if f of z equals y. And I mean, you can kind of see like that in one direction, because if f of x equals y, then if you set x equals y, you get a 0 here. F of z here, and you get a 0 here. So like 0 by 0, that can only like that. Yeah. So sorry. If the quotient is 0 at z, that can only work if this is also 0 at that z. So like so it can only really work if this is correct. But the other direction is slightly more complicated. So if we restate this, basically we get the fact that we get the polynomial that fulfills the equation, this equation. So we just put the x minus z on the other side. Q of x times x minus z equals f of x minus y, if and only f of z equals y. Okay, and now we get to how the KCG proofs work. So if a prover wants to prove that f of z equals y, they compute this quotient q of x, which is f of x minus y divided by x minus z, and send the proof pi, which is q of s, so the commitment to the polynomial q. And in order to verify this, what the verifier will do is they'll take this quotient and they will multiply it by the commitment to s minus z, and check that this is the same as our original polynomial, the commitment to that, minus y. And sorry, this is unfortunately not very readable on this background. Because if you write it out in this pairing group, then you get, on the right-hand side, q of s times s minus z in the target group equals f of s minus y. And this is the same as the second equation. So the cool thing is we can verify this equation because we are able to multiply two polynomial commitments inside using the pairing. And this way we can verify that the quotient was actually computed correctly. Cool. Yeah, and that is basically that is how KZG commitments work. So like just to so the idea is just if you can compute this quotient, then you'll be able to find something that fulfills this equation. And using the factor theorem that we mentioned previously, if f of z is not y, then you cannot compute this. It doesn't exist. It's not a polynomial, and we can only commit to polynomials. So yeah, this is the recap on the KZG commitment. We can commit to any polynomial using a single element in G1. And and this is just the evaluation of the polynomial at the secret point S inside the black box. We can open the commitment at any point, so we can compute f of z. And by computing the quotient q of x, we can compute this proof, which is q of s in the black box. And in order to verify that proof, we use this pairing equation, and that shows a verifier that this evaluation is correct. Cool. So that is KZG, how KZG commitments work. Now, I want to do something slightly more, which is a technique that we use quite a lot. We have even using it in EAP 4844. And so I want to give a quick introduction into how it works, which is the random evaluation trick. Okay. So basically, let's recall that KZG commitments are nothing but evaluating a polynomial f at a secant point s inside this elliptic curve black box. And so in a way, this is already like a random evaluation. Like, but basically what we've done is we've identified this polynomial using a random evaluation, and we somehow found that this is good enough to like to hash a polynomial in a way that it's very difficult to create collision. And more generally, this random evaluation trick can be used to verify polynomial identities. And the reason for that is the Schwarz-Zippel lemma. And I will just formulate it's a more general one, but let's say what it says in one dimension. So let's have a polynomial of degree less than n that is not identical to 0. So there's one particular polynomial that is 0 everywhere. That's just like all zeros, right? That's a very special polynomial. So let's say it's not that. Now let's take a random point z in fp. Then the probability that f of z is 0 is at most n over p. And that's because it can have at most n zeros. And so this is a very useful thing because our p is very, very large and our degree is relatively small compared to it in our case. So for example, for BLAS 12381, p is 255 bits. Say we commit to a polynomial of degree 2 to the 12, then this probability is something like 2 to the minus 240. So like it's a very, very small probability. And so here's the first way in which we can use this. So like we have these transaction blobs that we'll define for 4844. So it's like they are commitments to polynomials with 4090 4095. So in total 4096 points. And computing such a commitment is not very expensive, but it is expensive. It's like 50 milliseconds to do this. But verifying one KZG proof is quite a lot cheaper. It only costs about 2 milliseconds. So we can use this to our advantage. And so the idea is this. We take our commitment to the polynomial C, and we take the polynomial f itself. So what we want to verify is that we have the polynomial that it's given to us. So in this case, we have all the data, and we have the commitment. And in a naive way, we can just compute the commitment from the polynomial. But that's expensive. Okay, how can we do it cheaper? We compute a random point And one way to get a random point is actually a very cool technique. It's called Fiat-Shamir. We take all our inputs. So we compute that as the hash of the commitment and the polynomial. Why is that kind of random? Because like if an attacker tries to craft something, if they try to adversarially compute either C or F, it will always change the point Z. So it's very hard for them to find some like to craft them in a way that breaks our construction. So basically, this is a common technique in cryptography to get something random that the attacker cannot control. And so we evaluate this polynomial y at this random point that we've taken, and then we compute a KZG proof that f of z equals y. And basically, then what we'll do is we just add this proof to our transaction blob wrapper, which is the way we're sending transactions. And then, like to verify this, you compute z as this hash. You also compute f of z, which you can do because you have the data for that. And you check the proof pi, the KCG proof. And that's done. And that's much, much cheaper than computing the commitment. So that's one way in which we can use random evaluations to like save us a lot of work and making things more efficient. Okay. So here's another way in which we can use this random evaluation technique. So ZK rollups, they use many different proof schemes. And so only a handful, I don't know if actually there are any right now, will use natively KCG commitments over BLS 12381. And so the question is like, how do all the other make efficient use of our blob commitments that we want to add with 4844 and then full sharding? Because computing KCG commitments inside a proof or computing pairings, that is pretty expensive. Like that's a very expensive operation in a zero knowledge proof. And so what we do in this case is basically you have to you commit to the data in different ways. So we have three different inputs. So we have our blob data, which is this function f itself, and we have two different types of commitments now. We have C, which is our blob commitment, which is what we'll use inside Ethereum for 4844, and we have another way of committing to this data, which is using the ZK rollups native commitment. So they will, in some way, it will also have some way of committing to data that works well for the zero knowledge proof scheme. And so in this case, what we'll do is we'll take Z as a hash of C and R, like these two different commitments, and we will compute Y again as f of Z, and we'll add pi as a proof that f of z equals 1. And we'll add this precompile that allows us in the Ethereum virtual machine to verify that the KCG proof pi. So we will know that C is a correct commitment to F. And what we'll need to add is to add the proof that R is also a correct commitment. And the ZK rollup can do that inside the proof. So they will, inside the proof, they'll also have to somehow get C and R as an input and hash them and compute that. And then they can evaluate. So they will also have F because the rollup wants to use the data. So F is completely available to them. And they just have to compute Y equals F of Z. And use some technique to verify that the f is the same as the r, but there are ways to make this easy, and then they can verify that they have the same data as was committed through C. So that will make it much easier to use these commitments in ZK rollups. Cool. Yeah, I collected some resources if you want to read further on this. So Vitalik wrote a while ago a post on elliptic curve pairings. Because there was a lot of interest in that, I wrote some notes on how on this last part how to use KCG commitments in ZK rollups. For those who are like kind of skeptical and are like wondering, do we really need this like advanced cryptography and trusted setup and so on? Vitalik recently wrote a summary on like what the difficulties are with alternatives to KZG commitments. Here, this is if you want kind of, it's very similar to this talk, but I wrote a blog post about KZG commitments. And then, of course, if you want to dive deep, there's the original KZG paper. And if you scan this QR code, there will be all these links. Cool. Yeah.
So I guess we look at the box. My question is, if you look at the link fresh randomness.
I don't understand. Why? Where do you want to open it multiple times?
So what we do is basically just checking ultimate checking.
Right.
And in the life cycle of the pattern, the life cycle of
Right.
If each time you would have used the fresh randomness,
are you talking about S or like the trusted setup?
I mean, inside the
yes. Mm-hmm. Yeah.
So my problem is what if you have this S as
mm-hmm.
So because I didn't check because the students are not eventually probably
right. But this is a cryptographic probability, right? We're talking about, I mean, that's why we're setting the security to 2 to the minus 128. So 220, yeah.
I'm just saying that it's not like the
mm-hmm. Mm-hmm. Yeah. Yes, but so we are setting in cryptography, we are setting our security parameter already in the assumption that an attacker will do a lot of computation to try to break it, like 2 to the 50, 2 to the 60 or more computation power. This is much, much more than however we ever use it in the actual protocol. So like this is all already covered by the cryptographic construction. I mean, you can do it, but the random probabilities, like the probability of randomly hitting that, are extremely, extremely low. Like if you construct it so that the probability, so like randomly they are less than 2 to the minus 200 or something like that. It's like so low you cannot even think about it. Yeah.
You seem to be using evaluations to distinguish polynomials. I wonder how you distinguish something like x to the p minus x from the zero polynomial.
X to the p
minus x inverted p.
Right.
From the zero polynomial.
Yes. Yeah. No, you can't. But that's fine. I mean the. So the degree. Correct, but okay. So we are always, because we're limiting the degree of our polynomials, right? So our trusted setup will only go to a certain power, for example, to the power of 12. And inside that space, there's only the zero polynomial. Yes. Yeah. Yeah. So like if you have no limits on the polynomial degrees, then it doesn't work. But we always have a limit.
Yeah, the question could lead to
the
Q&A time. Okay. And next.
Thank you. Thank you. Excellent, excellent. Thank you, Danksharding, for the math. So, okay, so now we're gonna go into the bit more like, kind of like we're in the sky of math and we're kind of like tone it down into like the protocol stuff. So I'm gonna start with a small like explanation of how all this math stuff go into our protocol and how like, you know, all the extra bandwidth of 4844 travels around and gets verified, then Proto is going to take it and tone it even down into more practical stuff, like how the L2s are going to use the data. And then Ansgar is going to tone it even more down and basically explain how people pay for this data. So, okay. So basically, this is a graph that shows how like optimism and L2, what is its costs. And you can see that like this blue stuff is the data fees, like how much money they are paying for the like data they put on chain. And the other like white stuff is some other stuff. But you can see that the data is dominating all the costs. So basically what 4844 is, it's like a mechanism that drastically increases the amount of data people can post on chain. And this is all it is, right? So, okay, so basically what we want to do is we want to increase the amount of data. So on this very simple picture, on the left side, you can see our data, which we call Blob, because it's a bunch of data that also corresponds to a polynomial. And on the right-hand side, you can see a small thing, a commitment that represents that data, commits to that data. And the like rough idea is that, you know, commitment goes on chain forever, whereas the blob is kind of like, you know, there for a bit and then disappears. So this is like the high level strategy of how we increase bandwidth. We commit to data, we keep the commitments forever, but the data is ephemeral in a way. Okay, so let's talk a bit about what this data is, what these blobs are, how do polynomials enter this picture. So, okay, this is a polynomial. I think by now you're very familiar with it based on the last talk. The question is, like, how do we put data into this polynomial? And like, the basic idea is, you know, you have these coefficients, the A1, A2, A whatever, and you can basically put data into this coefficient. So, you know, if you have some data, 1, 4, 1, 6, you can put it in the coefficient, so you make this little polynomial on the bottom. And that's like a very straightforward way to put data into polynomial. So, right, so let's now think of like what, like in our case, let's see about these numbers 1416, how they can resemble real data. So in our case, the numbers are going to be finite fields. So they're going to be parts of a finite field, which is going to be like a number between 0 and this insanely huge prime number. And so each coefficient is going to be a number between these two things. And that's about 254 bits. That's about 31 bytes. So a coefficient with a polynomial with like 4096 coefficients can store about 128 kilobytes by putting the stuff into the coefficients. So, you know, now we know of a way to store 128 kilobytes into a polynomial. And that's kind of interesting because, like, you know, right now rollups, they don't even use close to that number. Like maybe they use 1 kilobyte. So we're basically giving lots and lots of space, maybe even uncomfortably lots of space to rollups to put their stuff in. But this is like the whole idea of 4844. Of course, in reality, we don't put the data into the coefficients and we put them into evaluations and then we do interpolation, but like, whatever, this is not so relevant for this case. The idea is that, like, you know, we encode data into a polynomial and we have polynomials that correspond to a big amount of data, and that's a blob, right? And, you know, then we have KZG, which is what Danksharding was explaining for the past 45 minutes, which is basically like a black box where you give a polynomial to the black box and spits out a commitment, and the commitment is tiny and the data is big. So you end up with a situation where, you know, you end up posting on chain lots of data and then a small commitment. And this is like the rough idea. So just to talk a bit about like when this data travels, what the network is supposed to do. Like when you see a commitment that corresponds to lots of data, what the network needs to do is like they need to make sure that the data corresponds to that commitment. And like the basic thing to do there, the basic strategy of the verifier to make sure that someone is not like, fooling us and giving us a wrong commitment to other data, which would be catastrophic, is to, like commit to P of X, use this black box again, commit to it, and then check that the commitment that the verifier computed matches the commitment that the guy gave you. So that's basically a pretty straightforward way to verify that polynomial matches the commitment. But then we have more data and more commitments. In a transaction you can have lots of those. In a blob you can have lots of those, and that starts being quite expensive. So what we end up doing, because like it's 50 milliseconds to do each of the commitments, and it scales linearly, so that ends up being quite expensive, especially for mempool and this kind of stuff. So in the end, what we're using KZG proofs and this whole random evaluation trick that Dankrad taught you before. And basically, for each like data and commitment, we also put a proof of a random evaluation. So basically, the proof is a helper that helps you do this small verification. I don't have enough time to go into the details, but like the idea is that, like the proof tells you that the committed polynomial evaluates to y at z, and then you can also evaluate the polynomial on the left side at z and get some other number, and if the y1 and y2 matches, you're certain that it's the same, that the polynomial matches the commitment. And this is much faster than doing the commitment manually. It's not my intention to go very deep into this. I'm just giving you some idea of how KZG is used in the protocol. So I think I'm going to stop here and stop with the cryptography and pass it over to Proto, who is going to go a bit deeper into the actual system.
Thank you. Hello, everyone. So let's talk about the Blob usage. So with EIP 484, we're introducing a transaction type to confirm these blobs in the EVM chain. However, something to note is that it's a new concept here where we are having a transaction type with data outside of the transaction. That's now responsibility of the consensus layer. So it's like a regular EIP 1559 transaction. Then the transaction contains some pointers, or hashes really, that then commit to the blob data. This is the transaction in a little bit more detail. Something else to note is that it's not RLP, but SSZ, so it merkleizes nicely, and it's better for layer 2. And then note here that we have these data hashes committing or to hashing the KZG commitments, which then commit to the full blob data. These data hashes are available in the EVM through an opcode, whereas the blob data lives outside of the EVM. So the blob content is, unlike call data, not available in the EVM. Eventually, we can prune this blob data. It's not a long-term commitment to store all of this blob data, but rather we are introducing this blob data just for the availability properties. A layer 2 needs this data to help users sync the latest state permissionlessly without communicating directly with the sequencer or whichever operator exists on the rollup. And then people can reconstruct the latest state. We can have a different solution for retrieving very old states, like a month ago or like 2 weeks ago. So there's the separation of data and the transaction itself. So this is what the lifecycle looks like. As a layer 2 user, you submit a transaction. Then we have this bundling. As a layer 2, we often combine the transactions, so we can pack them, compress them, and so on. This is a task for the rollup operator. And then as a rollup operator, you publish your bundle to layer 1 with this new transaction type. And then in the transaction pool, we have both the transaction that pays the fee, as well as the wrapper data with the actual blob content. And then the layer 1 beacon proposer creates a block, and the blobs make their way from the transaction pool in the execution layer to the consensus layer. At this point, the blobs don't get into the execution layer back. It's just the responsibility of the consensus layer. Pairs on the beacon chain, they sync the blobs, bundle together with blobs from other transactions as a sidecar. And then the execution payload stays on layer 1, whereas the blobs stay available for a sufficient amount of time to secure layer 2, but then can be pruned afterwards. So blob data is bounded. This is what it looks like on the network level. We have the layer 2 sequencer communicating with the transaction pool, the execution engine communicating with the beacon proposer, then beacon nodes syncing the blobs with each other, and then there's the split of the data where the other beacon nodes, they give the execution payload, process the EVM and everything. Fees will be processed by everybody, but the blobs, they stay in the consensus layer until a layer 2 node retrieves them to reconstruct the layer 2 state. So how do rollups work with this? Danksharding already explained the proof of equivalence trick. So I'll give you just a simplified overview how we do this in the EVM. We introduce two new things in the EVM, an opcode and a precompile. The opcode simply retrieves the data hash, which is this hash that is part of the transaction, just like the hashes in the access list from the Berlin transaction type. It can be retrieved through an opcode, pushed on the stack. And then there's this precompile, which you can provide with a proof to verify that certain data at a certain position matches the blob content committed to by the data hash. And in the case of ZK rollup, we use this precompile to do a random evaluation and prove that the data that the rollup is importing is equivalent, equal to the data that the blob is introducing. This precompile is versioned, so we can change the commitment scheme. And in the future, I hope we can use it for other things, perhaps Virtual tree verification. Then this is part 2. Yes.
Can you evaluate that for when the blob has been pumped ready?
Right, so going back, the proof, all the inputs to the precompile, they're passed in as call data. The blob is completely separate, is not involved in any of this computation. And so it's just the call data that we're passing in with a proof, the index of the point we're trying to evaluate, the commitment that hashes to the hash that we retrieve from the opcode, and then the precompile will verify everything. Similarly, we have the ZK state transition that needs to be verified. This is all ZK rollup specific. Up to you to design this. But with the data that's verified and the ZK proof that's verified, we can then get some outputs that we can persist and then use to enable withdrawals. And then this is the version of the interactive optimistic rollups. Interactive optimistic rollups use this concept called a pre-image oracle, where we do not access all the data at the same time, but rather we load pre-images one at a time. And by bisecting an execution trace, we only really have to do a proof for a single step, a single execution of a single VM instruction. And this might be loading some data. So for example, we start with a layer 1 block header hash, then we retrieve the full block header as a pre-image, then we retrieve the transactions by digging into the Merkle tree commitment in the transactions hash. And then we can get the data hashes from the transaction, and then from the data hash, we can get the cache decommitment, and then it's not a regular hash commitment anymore, but there's a different type of commitment with the same oracle, where we load one point from the blob that is committed to by the blob transaction. And so this way we can load all the data into the fraud-proof VM. Thank you.
Okay, yeah. Hello, everyone. I'm Ansgar. I'm going to talk a little bit about, now that we hopefully in the future will have this functionality, how can you pay for it, but also kind of conceptually, basically, I mean, the Ethereum blockchain is already, kind of pushing its limits, like where's the extra space resource-wise for this, basically, where does the efficiency gain here come from? And to understand that, first we have to just look in general about like how does resource pricing on Ethereum work today. So this is just kind of my way of thinking about like categorizing the different resources we have on Ethereum. So there's things like bandwidth, compute, state access, memory, state growth, history growth, right? This is all the kind of things, and this is a non-exhaustive list, right? But this is basically the kind of things that actually cause effort for nodes while they're processing a transaction. And if you squint at this hard enough, you'll notice that there are basically two different types of resources here, and we call those basically burst limits and sustained limits. And so burst limits are things where basically they cause costs or incur costs right at the moment that the block is propagated, right? The bandwidth to propagate a block, the compute to actually verify it, all of this. The critical point there is that basically it has to be bounded in order for blocks to still be propagated in a timely manner, and also for nodes to be able to verify them at all, right? They might run out of resources. The sustained limits, they don't matter so much block to block. Those are more things that accumulate over time. So that's state growth, history growth, these kind of things, where like a single block can't really make like produce too much damage there, but over time it just basically makes it more and more costly to run a full node. As it turns out, like if you look at this, there's some sort of structure to this, and you can actually reorder this a little bit. And it turns out that usually there's a relatively good matching between like a specific burst limit and a specific sustained limit. So bandwidth and history growth, kind of they correspond, right? Because the bigger a block is, the bigger, like the more bandwidth you need to propagate, but then also the more disk space you need to just keep it around for history purposes. And similar with state access and state growth, these kind of things. Now, specifically for 4844, right, what we are introducing is this new type of data. So kind of the resources we're talking about here is this first kind of row. So it's on those burst limit, it's the bandwidth, how big can blocks get, and then on the sustained limit, it's just like how much resource do you need to store kind of the history of Ethereum. And if you pay attention and if you basically looked into the API a little bit, you already know that like there is this limit in terms of history growth. We introduce this new basically a mechanism where blobs are only stored for a single month. And so this is basically why on the history growth side, we basically, it does mean that there will be some extra requirement for node operators, but it's quite bounded because unless normal history that today is stored forever, but even after there's this nice ERP for 4444, basically even after that, it's still going to be stored for a year. Blobs are only stored for months. So basically in terms of sustained limits, it's not basically it has like a very limited impact. The more interesting and also more tricky side of this picture is the burst limit, so bandwidth, and to kind of understand like what the situation there is and how 4844 fits in. We have to first remember that today on Ethereum, basically we only have a single gas price, right? Whenever you send a transaction, you don't actually specify how much bandwidth do I want to use, how much compute, how much memory. You just set like one gas limit, and then also like what kind of base fee are you willing to pay for this, right? And it's all basically mapped down into what you could think about it as like a single dimension for pricing. And that comes with basically very real trade-offs in terms of kind of resource efficiency. So if you look at this kind of stylized picture of just looking at two different dimensions here, they could be, I don't know, data and compute or data and memory or whatever, right? Two different dimensions. And basically the way the kind of the Ethereum gas works today, and that's purely for simplicity, right? Because it's very simple for users to deal with one dimension basically. But the way it works is basically that it is basically that those two resources compete for usage in a block, right? So you could imagine if a block is very full of compute, then there's very little room to put any data in it, or the other way around. And actually, if you want to like open Etherscan, for example, they for every block for the detail page, they actually give you the size of the block, and usually it's something like 50 kilobytes, 100 kilobytes, but like rarely more than that. But if you look at what would a block look like if it was like just full of call data, which is where all the data comes from, if we were all the way, like say on the lower part of the diagram, if resource B was data, it could actually be up to 1 or 2 megabytes, like, well, 2 megabytes basically of size, right? So what that means is we basically determined in the past that 2 megabytes per block are kind of safe, and the resource would be there, right? It's basically sitting there, but an average block basically almost like completely underutilizes data. And that is, again, just because it's simpler for us conceptually to price these things. So most of the time we are like very far up the slope there. And where do you want to be? Like what would be like the most efficient way of handling resources? Well, that would basically be this picture. So ideally you'd want to basically make these things be independently consumable, where you can basically consume the most amount of the highest safe amount of data that we think you should be like the chain can manage. But then at the same time, you should also be able to still do state access to the biggest, the highest amount possible, or memory or whatever, right? There should not be this kind of competitive nature to it. And this is basically where 4844 on the burst limit side gets its efficiency, right? Because full sharding, full Danksharding, we'll hear about it a bit more after this, actually does really clever things where people only sample the data, so bandwidth constraints go quite down. But for 4844, there is no fancy trick, right? Everyone still downloads all the data, so it's very real bandwidth strain. So the innovation on the burst limit side is purely trying to get to this upper right point, trying to actually basically make it so that the existing resource we already have today is just more efficiently utilized. And the way we do this is by going from, as I was saying, like right now, today, pricing is one-dimensional. And so what we introduced with 4844 is basically we go 2D. And this is how that looks like. So this is an open PR right now. It's not yet quite merged, but you can have a look. So like small details might still change, but I think the general direction is pretty set. And so the idea is we introduce what we call data gas, and as you can kind of figure from the name, it's not blob gas, it's data gas. The aspiration would be that like maybe in the future we can expand this to cover the entire data dimension, but for now it's only used for blobs, and we set it in a way where basically like 1 byte of blob will cost 1 data gas. And this data gas, importantly, basically is completely independently priced from normal gas. So it has its own 5059 style mechanism and that's where basically where they use, and I see Mario is not very happy about this because, like he has to implement it in Geth at the end of the day. But this is really important for the EIP because other than that, basically you wouldn't be able to get to this more efficient bandwidth usage. So what does it look like, and how can you think about it? Well, it's just similar to how 1559 already looks. So the way this is courtesy of Proto. I stole the slide. So every column here would be a separate slot. So the first slot, and in this case, basically the target amount of blobs would be 2. The maximum allowed would be 4 in a block. So the first block comes in, it has exactly 2. So nothing happens. The next one has 3, right? The red one, it's basically one too many. So the price would go up, and then the next 2 kind of like are stable again, and then one misses a blob, so the price goes back down. So it's like a very, like just like 1559, like you know and love it, basically. It is a bit different, or like basically it's under the hood. It works a bit differently. So here's kind of a bit more look at the details here. So first of all, of course, just we have a max data gas per block, right? Just similar to 1559, and the target that is half of that. transactions, these blob transactions, they specify an additional max fee per data gas field. So like how much are they willing maximally per data gas to have their transaction included. Importantly, you know, that this does introduce a little bit extra complexity for users, but users in this case are not actually users. Those are like big rollups, right? So basically them having to specify one more value, you know, fine. That shouldn't, like, if you can't do that, maybe you shouldn't be in the rollup game, basically. And so we, to keep the complexity to zero minimum, though, we did not opt for having a separate tip for this dimension, so we just reused the existing tip. And then one thing that where we deviate from 1559 a little bit, in 1559, basically, if the demand were to completely crash, theoretically, like one gas could be I think valued as little as 7 Wei, which is just the minimum after which basically updates don't go lower anymore. But so the transaction would basically be free. We don't quite want basically to make the lowest demand case of transactions here completely free. So we set a minimum data gas price that's kind of at least somewhat meaningful. So that's like 10 to the minus 5 ETH per blob. So of course it's priced in data gas, but it comes down if you compute the cost of a full blob to that value. And the last thing, and again, this is very technical. So like if you just want to understand conceptually how this works, don't care about this, but if you ever pull up the EIP and you might stumble across this and you might be confused. So actually the way we track this in 1559 right now, we usually track the base fee directly and then we update it every block. Actually, it turned out after we introduced it, like looking at it, it's slightly conceptually ugly because we always do these kind of, so basically there's some properties in the updating we don't quite love. It's a little path dependent and these kind of things. So so we moved to just a conceptually simpler way of tracking for this dimension, where we track the excess data gas that has basically been used over the existence of the EIP, right? So basically we just we have some sort of target that we want to be used, and then every block, if it basically uses more than that, we just add to this counter, and then every block basically uses less than that, but we're still above 0 in this counter, we just reduce the counter. Yeah, sure, if you want to. This is basically a header field, just like the base fee. Yeah. So yeah. So this is one additional header field. Good question. And actually, also you can see that because I just wanted to give you like an impression of what the kind of calculating the cost looks like with this header field. So as you can see, basically we have these kind of mock functions. If you want to get the fee that a transaction actually has to pay, it depends on the header of the previous blocks, similar to 1559. So you first get the total data gas that the transaction consumes, which is just data gas per blob times the number of blobs, and then you calculate basically the base fee, but we don't call it base fee because again there's no tip, so it's kind of unnecessary to have the base fee tip distinction. So we just call it data gas price. And so how you basically for each block you once basically calculate its data gas price, and you do that by basically taking in this excess data gas, and then we use this fake exponential function. It's a nice little tidbit. I don't know, maybe it's irrelevant, but it's still fun to talk about briefly. So like just because we want so maybe I can already go to the next slide to explain. So basically this is kind of how the pricing develops. It's like 1559, right? So basically if you were to continue to just keep basically using up all the data space in a block, not just the target, it would basically be on an exponential curve and would be more and more expensive. And you can see basically like 1,000 excess blobs. That's roughly, I don't know, something like 10 minutes or so. So within 10 minutes you'd really like have like super expensive blobs if it were to keep being fully used. Yeah, Marius again. So the nice thing about this is that it's basically a pure function in excess data gas, right? So it doesn't really matter if it was accumulated at the beginning or at the end. There will probably be a different, like in the beginning, it will probably be relatively cheap to use data gas because rollups are still kind of in the process of adopting it, so there's not that much demand. So basically, probably for the first first month or so, we'd be like in the very zoomed in left part of this picture. And then later on, once it's all basically fully adopted and people use it, we'll be like a bit more towards the right in this picture. But it's not like, this is not basically, because it's so reactive, it's similar to 5059. So basically every block can at most do a 12.5% update. So the difference here, like basically you can go from one of these paradigms to the other within 5 minutes of high usage or low usage blocks. So it's not like, it's not basically something where it matters immensely what was done in the past. Basically a high consumption in the past only means that like basically you have like 5 minutes of reduced blob usage before you're back to your normal price level. So it's not, yeah. So basically, there's no significant kind of accumulation effect or anything, right? Right. Sure. No. But the thing is, because so the way to think about it is like, because the price is a pure function of the excess data gas. So at any excess data gas, I mean, of course, I put down excess blobs just to think about it more easily, but it's tracked in excess data gas. But once you reach something like, say, I don't know, 1,000 excess blobs, that would mean that sending one blob already costs 30 ETH. And that doesn't matter whether the excess blobs were accumulated over one day or if they were accumulated over a year. So basically, once the data gas field reaches that value, it would cost 30 ETH per blob to send blobs. So we would expect, of course, that rollups are not willing to pay that much for blobs, right? So if for some weird reason there was some spike in demand and the excess would shoot up to that level, it would quickly come back down and stay at some kind of permanent level. So the excess is not something that will continue to grow over time. It'll just, similar to the base fee. The base fee doesn't just grow over time. It just finds its equilibrium value. And of course, sometimes goes up and sometimes goes down temporarily, but it hovers around some sort of, 10 to 100 gray level-ish. And similarly, the excess blobs, because that can go back down, right? If a block uses less than a target, the number goes back down. So it will just find some sort of equilibrium value that corresponds to some sort of equilibrium price, and it'll just hover around that. Yeah, I'll just keep. I feel like we're out of time, unfortunately, for the sorry, fee market section. Yeah, come find me after for continued questions. So anyway, so basically this is how we make FOIA4 work. History growth, not a big deal. Bandwidth, we really need to put in work to make this work, and this is kind of where the core innovation of the ERP for now lies. Other than that, it's forwards compatible full Danksharding, but for now, this 2D fee market is really why we can do this and why we basically just utilize existing Ethereum resources more efficiently. And with that, I think we are done with the kind of the FOIA4 part of today, and we can move to full Danksharding. Do we? But that's not me talking about it, so someone is missing up here. I assume the man himself. So let's see.
Okay. Yeah. Cool. So I will be taking on the math again. So I don't know how much more capacity you have for that. Sorry for that. KZG is what that should say, but sure, we can reorder the names as well. So, okay, I want to introduce now to the two-dimensional KZG scheme, which we will need for full sharding. Sorry, this is a big jump. Okay, so when we do full sharding, why do we not take all the data that we want to encode and put it into one big KZG commitment? And the reason for that is that that is going to require a super node, like some powerful node that you probably can't easily run at home unless you like have a very good internet connection and want to invest some money into it. So you will need this both to construct blocks, where we're probably like kind of okay with it, but we will also need it to reconstruct the data in case there is a failure. And this is an assumption that we want to avoid for validity. So like it's kind of more acceptable if a failure leads to just not being able to construct blocks, or maybe we have to make smaller blocks, or we have to make blocks without sharded data. But it would be really bad if the absence of the supernode could lead to a network split where some people think data is available and some people think it's not available. This is what we want to avoid. So what we want is a construction where, yes, like there will be a lot of data in the network, and maybe like someone needs to be there specialized into distributing that data. But once they've done their job, the very decentralized network of maybe your Raspberry Pis at home can guarantee that it will always converge, it will always be safe, and so on. Okay. So what if we just use many different KZG commitments, just a list of KZG commitments. So if we do this naively, we just take many commitments and we sample from each, then we'll need a lot of samples because we before had this number of samples, for example, say 30 samples. Now we need 30 samples per commitment. Okay, that would be a lot of samples. But there's another much cooler way of doing this where we use read Solomon codes again, and we will extend M commitments for like M actual payload blobs and extend them to 2M commitments. So here's how this is going to work. So we have our original data commitments, in this case, 3 commitments. And what we'll do is we'll define another 4 commitments that are an extension of these commitments. So they will be completely determined by the actual data commitments. And yeah, so here's the math of how this works. So what we'll do is we'll define a 2-dimensional polynomial for the data. And it works the same way as before. So basically we will interpolate this polynomial. We will define it by this data region, the original data that comes from many different transactions that included sharded data. And what we'll say is, for simplicity, I'll just say the row k will just be the evaluation of this polynomial where we set y equals to the num of this row, y equals k. So we evaluate the polynomial at k, and then we get a 1-dimensional polynomial, right? So we get fk of x equals to this, and like you can pull all of this together, and what you get is again an expression just in these powers of x. And then we can commit to those polynomials in our normal KZG way. Okay, so we have fk of s equals to this. Now we replace the x by s and some complicated sum in there. But overall, we have like one elliptic curve element, this black box evaluation. And we call this c of k. Okay, now the cool thing is if you look at this expression as a function of k, then this is also polynomial, right? It's just a sum of terms of powers of k. Okay, so this is very cool. And what this means is that our commitments themselves will be on a polynomial. So if we see the commitments, which are now elliptic curve points as a function of k, they are on a polynomial. So what we have is, before we started with having each row being a polynomial that we commit to, we also have that each row, I mean, this is a property of just a 2-dimensional polynomial, each column will be a polynomial, but also the commitments themselves are a polynomial, in this case of degree 3. Yeah, because they're determined by these 4 commitments. Okay. So what we have is how the 2D commitment scheme will work is we'll have 2M row commitments, and we can actually verify that this is the cool thing. Like anyone who validates these commitments can easily verify that they are on this polynomial using a random evaluation trick again, which I introduced earlier. So what we'll do is we'll take the first M commitments, evaluate them at a random point, and we'll do the same for the second M commitments. And if these two result in the same actually the point will be, in this case, an elliptic curve point, then they are actually on a polynomial of degree n-1. For those who are interested, there is a way to do something very similar using 2D commitments. So you can do one commitment to the whole thing, but I won't go into the details here. But there are basically some downsides, but which is why we're not choosing that way. Cool. And so why are we doing this? Okay, so we have properties that we already know. We can verify all samples directly against commitments. There are no fraud proofs required. But now we need a constant number of samples for all these commitments in order to get probabilistic data availability. Basically, we get the property that if at least 75% of those samples are available, then all the data is available. And it can be reconstructed, and that's the cool thing, from validators or other nodes who only observe rows and columns. So there's nobody in the system will ever need or will be necessary. I'm sure they will exist, but it's not necessary that anyone watches the full square of samples in order to get these convergence properties. So what you'll notice is that this number is a bit higher than before. So like if we only have one commitment, then we only need 50% of the samples to be available. For the square, we need 75%. So the number of samples you'll need to get this will be a bit higher. Cool. And so what we get with this is that I made a proposal. I mean, this is all still in discussions, but like one of the ideas how we could extend this to a full sharding construction is that basically the way validators use this construction is that they will download rows and columns. They will each choose two randomly of each. And then what we get is that if a block is unavailable, it can't get more than 1/16 of attestations. So automatically the consensus will never vote to unavailable blocks. And at the same time, they can use these full rows and columns that they download to reconstruct any incomplete rows or columns. So if any samples are missing, they can reconstruct this. And because there will be some intersections, like for each validator, there will be, if they do two, like there will be these 4 intersections, they can seed the orthogonal rows and columns with the samples that may be missing. And so like as an example, I made a computation that basically with about 55,000 online validators, you get a guaranteed reconstruction where basically every sample will always be reconstructed if like we initially had enough data available to do this. And this in practice, this number will be much smaller because most nodes don't run one validator, but tens and some even hundreds. And data availability sampling, yeah, it's basically just checking like random samples on a square. And what we want is, again, we want to get that the probability that an unavailable block passes is less than 2 to the minus 30. And if you do the math, you find that you need about 75 random samples to do that. And so the bandwidth to do that in this example, if we do 512 byte samples, would be 2.5 kilobytes per second, which is a really nice low number. Cool. Okay, handing it to Danny.
Thank you. I need this. Okay, so there's a lot of math, and there's an elegant construction, assuming that we can do a constant time amount of work for a large amount of data to kind of layer it into it as similar to like a validity condition on our block tree. We don't consider invalid blocks in our block tree. We don't consider unavailable blocks in our block tree. And so the math and the construction are very elegant, but when the rubber meets the road, data availability sampling on the networking layer is actually a non-trivial problem. That's the wrong way. Oh, the arrow that goes right is so worn it doesn't look like an arrow anymore. Okay, so kind of stepping back, why are we making this problem hard for ourselves? Everyone's seen this. These things it's not fundamental that they cannot come together, scalability, security, and decentralization all in one system, but it is hard. And it's hard primarily because we want home nodes to be able to run. We want standard computers to be able to validate the system, to kind of have security and aggregate even against a malicious majority of our consensus participants. Again, kind of in that validity condition of if there's an invalid block and all the validators or miners are saying that's what the head is, you say, well, that's not even literally real because it is invalid. And so users in power kind of define what the network is. Similarly, we want to do that with our bandwidth consideration with respect to data availability. So thus, we need to focus on the bandwidth here. A lot of this is a quick recap. We've been talking about this all day, but we need to scale execution. We need to scale data availability. Essentially, rollups give us some sort of like compression algorithm for the execution of transactions, whether it be from fraud proofs or validity proofs. Data availability, we use DAS, data availability sampling, or we want to. Data availability, we've been talking about it all day, means no network participant, including supermajority of full nodes, has the ability to withhold data. Again, it kind of makes data availability a validity condition. It is already today, as we noted, you have to download full blocks, but once it's a lot of data and we want those home nodes, it becomes very hard. Right. So again, we want the amount of work to not really scale as those blocks become very large to scale the network. So data availability, assurance that data is not withheld. Also assurance that data was published. Real quick shout out. Danksharding made most of these slides for another talk, and I'm just reusing them. Important to note, it's not data storage, it's not continued availability. There's a debate as to how long the network needs to have the data available so that people can check that it was made available. Some people say on the order of, where are we at, like 100 seconds? Some people say 2 weeks. It kind of depends on the use case, and it's a bit of more of a UX debate. It's kind of the onlinedness requirement of people to be able to get this security guarantee without trusting someone else. So is it important? I don't think we need to get into this too much. Optimistic rollups and ZK rollups, it's critically important. And who knows? The utility of solving this problem might extend beyond these two types of systems. So the networking's hard, and we probably are making it even harder on ourselves by some of our assumptions here. So we could say, okay, we certainly want to make sure that block producer and consensus nodes, we want to be able to not be fooled by a malicious majority, but maybe we have a neutral PDP network and we can just assume that the PDP network is like healthy and gives us what we want. This is certainly attractive. It ensures that each node really can see that they get the statistical security. But if we're assuming that the validators can be malicious, it's a very high amount of them, at least maybe that 2/3. Some people like to say 99%. Depends on probably the construction on what the real one is. Then the assumption then that the network is neutral is probably not a realistic assumption. So, well, maybe it's realistic in most scenarios, but if we want to really be able to harden against that majority adversary, we need to be thinking about an attacker-controlled P2P network by some threshold, defining whatever that is. Again, this is a lot of kind of exposition of the problem rather than total solutions of the problem. So, if I'm thinking about designing data availability sampling, it's probably interesting to think about what's a good neutral network solution, but then I think when the rubber meets the road, we need to think about what thresholds can we actually harden against a very attacker-controlled P2P network. So in this model, certainly some nodes can be fooled, and so it ends up being a collective guarantee, again, depending on the thresholds and how this system is tuned. But rather than no node can be fooled, it's probably going to end up looking like no above certain threshold of node can be fooled, maybe for a certain period of time, maybe until the network kind of resolves itself. But so this is likely the correct model. but it does make the problem harder. So the P2P problem, what are we trying to do here? We want this like P2P distributed data structure that can reliably serve samples so that people can do their job of getting the samples. We want low overhead on nodes from multiple perspectives. One, on nodes that are participating in pulling down samples, but also potentially want to leverage nodes that are not just validators, not just builders in this distributed P2P structure. So we want to also consider the overhead of these nodes that are participating in the serving of the samples as well, or in the dissemination of the samples, other things. I want to be robust against attacks. I think one of the really, really scary things here is liveness attacks, DOSes, Sybil attacks, et cetera, that are happening on the network layer. Because if a majority of nodes are seeing data as unavailable, either temporarily or permanently, then they cannot follow the chain at all. Again, we want this to be essentially a validity condition. You know, if there's an invalid transaction in this branch, I don't follow the branch. If that branch is unavailable, I don't follow the branch. So that is a very important, critical requirement, but a very terrifying requirement, meaning that like it is very important that these P2P structures are hardened and we do understand kind of their failure modes. We understand where they operate, and we do understand how they resolve maybe after an attack. And low latency on the order of seconds. I have a page of some desiderata we can get into in a second. And there's some distinct challenges, I think, when you're kind of thinking about this problem. Dissemination into the P2P structure. We have a lot of data. How do you efficiently get it into this P2P structure without causing high load on the individual nodes of the P2P structure? So if every node only needs 1/100th of the data, but they had to touch 50% of the data to get it disseminated in the structure, we're kind of missing something there. Similarly, we want to support queries of disseminated data sample for X amount of time, which I can get into the desiderata again. And validators, certainly with their row and column kind of cryptoeconomic duty, can identify and reconstruct missing data. But we also probably want to consider, should this P2P structure be able to identify and reconstruct missing data? So there's two kinds of potential reconstruction that we might want. So validators are very incentivized out the gate, if things are missing from their rows and columns, to incentivize to repair, patch, and make things whole. But if, say, the P2P structure is supposed to serve data availability sampling for 1 week, then are those validators the same people that will then identify and reconstruct missing data, or is there some other more distributed and less timely required method to do so? There's a handful of actors involved in data availability sampling. Francesco is going to talk about builders and where they fit into kind of the consensus protocol, but they're kind of the original source of the data. They're highly incentivized to get it out, but they're probably not one that you'd want to rely on in perpetuity. Validators, these are crypto-economically incentivized actors that we can try to leverage in this construction. They do have the rows and columns. They do also perform data availability sampling, like a user node. And then we have users. Users perform data availability sampling. Hopefully, they can be leveraged in serving and making the whole P2P also more resilient itself. Some quick desiderata. Right now, if I were thinking about building data availability sampling, if I'm researching and doing stuff, these are kind of some target numbers, but I would also be sweeping these numbers and understanding where they work and where they don't. So data size, 32 megabytes per block. That's per 12 seconds. Or if the slot time were adjusted, it might be per some other amount of seconds, call it 16 or 20. But with the 2D erasure coding, that ends up being 128 megabytes of data being disseminated into the network. Chunks, I think there's chunks and we sample the chunks, or there's samples and we sample the samples, but on the order of 250,000, you can make these larger, but then you end up with, you still need the same constant number of samples, so you end up with more overhead. Samples, he said 75, something on that order, but essentially we want to drive that probability down as we're doing the sampling. Latency, validators really right now need to make decisions about what they see as the valid and available head on the order of 4 seconds. that could be tuned depending on the constructions available to us. But if they could not regularly be able to do data availability sampling, then on the order of 4 seconds, we have a problem. Users, you could have a potentially more lax requirement on the order of 12 seconds, on the order of a slot. Or you could even consider maybe they needed to be doing it on the order of epochs and optimistically following head as available. And maybe there's some play in the constructions there. Validator nodes, 100K is pretty optimistic, but we probably have on the order of 4,000 today. So something on that order is kind of the baseline. And then user nodes on the order of 10 years, especially if you start adding lighter weight nodes with statelessness and light clients that might want to participate in this data availability sampling. 100K to 1 million user nodes. So it's really, if the user nodes cannot participate in the serving of samples, then the load on if we only relied on, say, incentivized actors like validators, then the load would actually scale as to serve as the user nodes serve. So it's probably very important to tie them into the data structure itself. Bandwidth assumption, I don't know. It's probably worth discussing. The ETH.org website suggests a minimum of 10 megabytes per second to run a full node, but for good whatever, 25 megabytes per second. I don't know who came up with that number. Maybe it's a good place to start the conversation. And then persistence. Obviously, like I said, data availability sampling is not for persistence. It's to ensure that data is made available. But if data was made available for half a second, like no one's going to necessarily be able to prove that to themselves that it was made available, or a very small subset. So is it 2 epochs? Is it 2 weeks? There's much debate here. Ansgar, I think, what was your recent number? Is he still here?
Something between 10 minutes and an hour.
Okay, 10 minutes and an hour. Whereas I think some are more like a week, 2 weeks, and that actually changes the requirements on nodes, especially in terms of storage. My intuition here is that the online-edness requirement for users that want to get their state transition changes from ZK rollups, or policeman users that want to submit fraud proofs for ZK for optimistic rollups, this dictates their online-edness requirement. And so I feel like 10 minutes. Oh man, I gotta get out of here. Okay, cool. So debate. An hour seems short. P2P designs. So one easy thing you could do is just say there's a bunch of super nodes on the network, and if you connect to them, you do DAS, and if they give you the samples that you want, then things are available. This is, I believe, Celestia's current design, although that statement I could claim is true a few months ago. I'm not sure today. And you could potentially do something similar in Ethereum, whereas maybe instead of each node needing to have everything, you could leverage Ethereum validators, the rows and columns that they custodied, and it looks kind of similar. This is nice. If you connect to one on a supernode, then you get what you need. But this doesn't really fit well into the node model, especially if validators, a node that's running on the order of 1, 2, maybe 3 validators should be able to run on the order of, home resources, which is definitely not the case. DHTs. They all of a sudden, DHT's nice way to distribute data in a distributed data structure across the network. It's a nice way to find data, and seems intuitively like a very good direction, a very good start. It fits really well in because each of these nodes can have a very small amount of data, and really nice scalability. As you add more nodes to the network, you can, depending on your redundancy factor, you can have similar or less data per node. Prone to liveness attacks. It's really easy to Sybil this thing naively. You just make node IDs, you fill the tables, and if you're a malicious node, you can just return entries from your table that are full of malicious nodes. And one thing that's, I think, very promising is looking at secured DHTs. Dankshard's been digging into Echidna, and I believe there may be some others in this room that have looked at some other papers about hardened DHTs. And we do have, as long as you have a SIPL-resistant set, then you all of a sudden can have certain guarantees in these constructions. So you can leverage the validator set or maybe other types of cryptoeconomic sets to have hardened DHTs. So you could use standard OpenDHT for average case performance and maybe a secondary or fallback DHT, leveraging the validator set for in case of attack. You could also, yeah, there's some weirdness because then all of a sudden you're assuming that you have a certain amount of honest validators for this. So does that suffice under the malicious majority construction? Sure, you can probably tune the numbers, but you could also potentially layer other types of cryptoeconomic sets, proof of humanity, spruce ID, whatever the hell, all sorts of stuff, and could have layered DHTs where they're ultimately just kind of fallbacks in the event that the big main DHT starts failing. Validator privacy and optionality and how they construct their node setups is probably very important. I'm definitely over time. Okay, cool, great. Oh, and there are actually a handful of people in this room that have grants from the EF to dig into R&D around data availability sampling. If you are interested in this problem, this is a critical problem to solve and work on over the next 12 months. Talk to me or email grants program at the EF or something. Thank you.
Hi, I'm Francesco, and I'll cover the last bit of this very large topic that we've kind of gone over today. It's proposability separation. I expect probably most people will be somewhat familiar with the concept, but this will be kind of a light introduction. Like it's not going to be it's not going to be too advanced. It's going to be just for you to get a picture of how does it fit with Danksharding and what does it have to do with it in general, and also like kind of how does the roadmap of that fitting in the protocol look like. Yeah. So first of all, what is PBS? It's sorry. Yeah, so there's let's start from the pieces. We have P, B, and S. So first of all, block building, the B, is essentially this task of actually creating and distributing execution payloads mainly. So we have beacon blocks, but then inside them there's execution payload, which is the kind of the valuable part in some sense, the part that actually changes the state of the execution layer. And this is the part that is kind of requires some specialization to deal with, whereas the beacon block part is more of a consensus part. And yeah, so this is normally today we only think about the creating part, like only basically putting together a new execution payload, but the distribution part will also become critical, especially in the context of Danksharding, and also this so the distribution will involve the data that is committed to, which is going to be eventually very large. So that's why it's kind of an important task eventually. And so for these reasons, and well, later we'll get a bit more into them, it's a quite specialized activity that we don't really want normal validators to do because it would kind of increase their requirements too much for us to be comfortable with. And then there's proposing. So this is just you could think of today proposing includes both things, both this kind of consensus part of making a beacon block and including all the consensus messages in it, attestations and other things like slashing messages or anything that's kind of critical to the good functioning of the beacon chain. But then also the putting an execution payload in it. So today it's still possible for anyone to do this by themselves and kind of have both the roles together. But if we kind of ignore this execution payload part, this is really not a particularly specialized role, and we think that it's always going to be possible to, or we really want this to always be possible with low requirements, basically what we expect today validator to have. And yeah, the separation is just that these two things are split up. Like we don't, the default, it would not be anymore that a validator does both things, or a proposer, which is a validator, does both things, but that the proposer does the beacon block relevant part, the consensus messages part, and some other kind of specialized actor comes in with the execution payload and the distribution of the data eventually. And yeah, so why do we want to do this? I've kind of already hinted at it, but yeah, it's simply that if we outsource the specialized stuff, we can keep the simple stuff basically decentralized. We can keep the really consensus critical things essentially done by a very decentralized validator set, which is a really important goal in Ethereum in general. So, and I mean, practically, why, what are these things that we want to outsource? So for the whole day we've been talking about Danksharding, and there's nothing really, I guess, fundamental about sharding that requires this outsourcing. You could imagine other models. I mean, I guess original sharding model before the Dank part didn't require this outsourcing, but it's really like a major simplification. And so I mean, not just a simplification, also has, I think, like consequences for latency. Like it just makes it gives us this really tight coupling between the execution payload, the blobs, and kind of yeah, just streamlines the whole process. And so with Danksharding, if we do want these simplifications, we kind of have to we start having something to outsource, because the proposer has to compute these commitments really quickly, which is not easy to do for like normal hardware. And also, like probably the most prohibitive part is the basically distribution of the data to the network. So that would require like really kind of not acceptable upstream requirements for validators, like more than probably multiple gigabits and so yeah, we don't want to require this. It's like orders of magnitude more than what someone would need today, because basically the most you might need to distribute is 128 megabytes per block. And yeah, but again, this is not a kind of fundamental reason. If there was no other reason that we needed this separation for, we might be a bit more skeptical about Danksharding. We might think, well, we don't need these other actors. Why are we introducing them in the system just to get some simplification? That's not kind of the ethos of Ethereum. Like, we really want everything to be as decentralized as possible, as like resilient as possible. These actors probably do introduce some complexities in this vision. But the issue is Danksharding isn't the reason why we introduce these actors. The reason is MEV. And this is kind of a fundamental reason. I don't think anyone that has looked into MEV enough thinks that there's any other way essentially to go. And the issue is simply that, as I said, these execution payloads are really valuable, and extracting value from them is a really sophisticated activity from many points of view, algorithmic, infrastructural. Like, it requires potentially very good hardware, a very good connection. Like, latency is really important. So there's like all kinds of reasons. Oh, and also like access to order flow. So today we can think that order flow is more or less essentially access to mempool transactions is more or less available to everyone publicly, but it seems very naive to assume that that's going to be the case in the future, and already it's not quite true that that's the case. So maybe there's always going to be a public mempool for censorship resistance reasons, for other reasons, but it's really naive to think that everyone is going to have access to the same kind of raw material to build blocks, like the transactions. And this access to order flow is a huge part of being able to create valuable payloads. So there's like all kinds of reasons why it's just not realistic to think that validators will be able to profitably make their own blocks. And so there's these really like strong centralization pressures if we essentially don't provide them a way to do it. You just go and have someone else do it, well, which is the whole point of the separation. But there's different ways in which it could happen. Some ways in which it could happen are, for example, just everyone staking with pools, because that's the only way that they can extract value. Although that's actually kind of not already, it seems like a scenario that in some sense maybe we can avoid. We already have PBS today. Like, we usually say PBS and we mean basically in protocol PBS, so where the protocol kind of knows about the separation, like has a concept of builder, and in some sense like negotiates this outsourcing. But today we basically have PBS, is just not in protocol. It's called a MEV boost. Probably a lot of you know it. And essentially what it does is it introduces a trusted third party in between a builder and proposer, which are these relayers. I don't think I have time to like go into the details of it, but essentially, we want builders to not trust proposers. We want proposers to not trust builders. There's reasons for that. And yeah, we just basically put like a trusted third party in the middle, which kind of negotiates the exchange. So the proposer wants something from the builder wants to get something to the proposer. The trusted third party makes sure that the exchange happens in a way where none of the two parties can cheat each other, essentially. And so this already exists today. A lot of the Ethereum blocks are built in this way. So it's the reality that, and it's not something that the Ethereum community kind of made, well, it is something that the Ethereum community made happen, but it's in some sense inevitable. Like anyone could always build some infrastructure of this kind, and people could use it if it's more profitable for them. So yeah, so we already have this. Why do we care about potentially putting this separation in protocol? So as I said, relays are trusted third parties. We don't usually like to have these sort of entities in the protocol. They're not critical in some sense. Well, if things are set up properly, which I mean, I think there's a lot of improvements to be done on the infrastructure that exists today. It's very young infrastructure, but either way, there's always going to be some kind of failure modes that we don't really like, or some requirements that we don't really like from having these parties. So one is that you have to basically whitelist them because they're trusted. So everyone has to kind of go and configure some list of these entities that they're fine with, essentially, that they trust. And we don't care if builders do that, but we don't really like validators to do that. Or, well, I don't know, that's debatable, but anyway, I think there's a future for relays to still exist and just have a fallback in protocol that is not the default, but that's a conversation for another time. But yeah, another thing is that today we don't really have a kind of live monitoring for relays. Like locally, people don't have a chance to observe interactions that relays have had with other proposers, and then disconnect from them if these interactions look suspicious, essentially. So that's something that we can include. We can basically really improve the the resilience of this whole system, because we can make it so that people don't need to go on Twitter and find out, oh, this relay is malicious, I'm going to disconnect from them, but just maybe this can happen locally, essentially. So there's a lot of improvement there, but still there's some kind of I guess really fundamental catastrophic scenario that seems unavoidable to me if we keep having, or rather, if we only rely on these entities for this outsourcing, if we have kind of no fallback. So especially with Danksharding. So today, you could always have a fallback. Actually, it's not so fundamental to the state of things today. You could always have this fallback, which is essentially the catastrophic scenario is like all relays that most people are connected to fail for some whatever reason. They're malicious or they're attacked. Anything could happen. They fail, and now all of a sudden, today it's fine. You could, once you manage to disconnect because you realize, okay, these people haven't given me blocks for however many times I've tried, or if you have this monitoring system, that's fine. You just fall back to you building your own, Geth or whatever, like other execution client you're running, building your own blocks. So now where liveness is not really threatened. Maybe it's like a temporary thing. But with Danksharding and also statelessness in some sense, if let's say all the validators are stateless, they cannot build their own blocks, or with Danksharding, like they cannot distribute data, then this becomes like a threat to network liveness. With Danksharding, not exactly. It's like you could make blocks, you just cannot put a lot of data into them, but you could argue, well, is that really liveness? Like if all the rollups kind of stop because they don't have access to data anymore, that is not really what we want. Yeah, so this is maybe what it will, well, this is like one of the current ideas of what it could look like to put it in protocol. I think, well, yeah, I think probably can't really go into it. I don't think we have time to go into it in much detail, but basically it looks like, as I said before, what are the relays? They're just these kind of actors that negotiate the exchange. What do we do if we want to remove these actors? We basically have the protocol negotiate the exchange. And the protocol in this case is basically other validators. So there's a proposer, there's a builder, and we have the whole rest of the validator set, or some committee, more, well, likely, that basically kind of makes sure with their, well, they observe the exchange, and with their attestations, they sort of make sure that if the proposer tries to cheat the builder, they fail, and vice versa, essentially. So it essentially gives us the property, for example, that if the proposer accepts some block and or some like bid, you could say, from a builder, and we have good latency, like kind of things are fine from a fortress perspective, from a network perspective, then the proposer will get paid. It doesn't matter what the builder does. If they reveal their block, good, kind of this is a good case. If they don't reveal their block, they reveal it late, tough luck for them. They're going to pay the validator and not even get their building opportunity. And so this is one design. There's this other design which is kind of interesting. Oh yeah, also thanks to Vitalik for all of the things. I just took him from many of his ETH research posts. But yeah, like, so this is basically, you could say in protocol map boost, because it's really like designed to look like map boost. Again, we have basically this like party in the middle, this time more clearly than before, which is in this case a committee. It also was before, but anyway, and this kind of party again negotiates the exchange. We could think of the party as basically an availability oracle. So it's basically its job is to ensure, it's to give guarantees to the proposer that what the builder sent is available. So the proposer will accept a header, like a basically offer of, I want to give you this block, pay you this much, and the builder will essentially erase your code. So, hopefully if you've followed the discussion, you know what erasure coding is by now. Essentially the execution payload to the committee, essentially encrypt, erasure code, then encrypt, and then basically split the parts to the committee, so that if some threshold of the committee is honest and online, they will be able to decrypt, even if not all of the committee is. And basically the committee signs, essentially individual members of the committee will attest to the fact that they have their part, so that if you see enough attestations and the committee is sufficiently honest, then you know that as a proposer that this thing will be able to be decrypted, and the data will be there essentially. So actually, yeah, this kind of fits in quite nicely with these data availability discussions. Like that is really the problem here, that the proposer is accepting a bid, but the builder doesn't want to say what the bid is, because that's their kind of private, like secret information. And we want basically some guarantee that even if you don't know what it is going to be there once the time comes, essentially. Like once you've accepted the bid and it's ready to go in the chain. So that's what it looks like. And just last, quickly, I want to comment on basically, so there's like censorship resistance questions about PBS, and I think they're not, they're like fairly well understood. There's clearly like a way that PBS in or out of protocol, so it doesn't really this is like, our questions also today. It does degrade censorship resistance, but we already know kind of how to deal with that. There's this concept of inclusion list. There's like slight tweaks of that. There's like basically really wide design space of very like roughly said ways for validators or proposers, but you could just say validators, to basically make sure that transaction that should go in the chain eventually get in the chain, even if builders don't want that. And this is also, by the way, like a really important reason why we want decentralization of the validator set, because if you don't have that, then you just don't have this option. Like if you have 100 validators and they don't want something to go on the chain, that's it. There's no way, there's ways like soft forking or, other ways, but there's no kind of automatic way to do that. Whereas with a decentralized validator set, we can always do that. And yeah, so inclusion lists are quite simple in some sense. There's like disagreements about how exactly they should work, but they're sort of simple today. So if we have like the property that it is easy for a validator to say this transaction is available and this transaction is valid. So the validity part becomes a bit harder with account abstraction. So there's some questions there, but we won't go into that. That's not really relevant here. The availability part, that becomes a bit harder with Danksharding, because now all of a sudden, there's all this like all these blobs floating around the network. There's all this data that you're not supposed to know. You're not supposed to essentially download all of. You're only supposed to sample what actually ends up. Okay, yeah, well, I'll just finish this phrase and then I guess that's it. But yeah, basically, so with Danksharding, determining availability becomes a bit harder. So we would like to have some kind of sharded mempool construction, so that you can, even for things that have not been included in a block yet, you can still in some way determine that they're available without everyone having to download everything, essentially. And at this point, and this might not need to be the default route that all transaction goes through, and probably won't, for kind of some of the reasons that I've already hinted at before. Like it's unreasonable to expect that everything will go through a public mempool, but this is kind of the fallback for censorship resistance always. And so we want to basically have some kind of construction like this. And I think that's it. We're out of time. Hopefully, maybe we still have time for some questions for everyone. Yeah, but otherwise, that's it.
Okay, so we are obviously out of time, but we can still use this room for another 20 minutes. We have a special guest here, Vitalik, here to answer some questions around it. Okay, any questions? Oh, okay. There's a question.
Hello, thank you. How do you approach the topic of multi-relay in this Danksharding like ecosystem? Because there are many solutions.
What do you mean by multi-relay?
And because I heard in PBS, but that it weakens the topic of censorship. But how do you approach the to improve the mempool with multiple relays of
So
information?
relays are a concept that exists in like MEV-boost kind of out of protocol PBS, right? Like it's not a concept that exists in protocol PBS. So the long-term solution is to, I think, to not need to rely on them. Mm-hmm.
Hi. The erasure coding and Shamia's secret sharing scheme seem very related.
They're the exact same math.
Okay.
Is network persistent for the blob is going to be dependent on finality? Because I would have expected this to be the case and therefore rule out completely these notions of having them for only 5 minutes.
What do you mean by dependent on finality? Like
that if we're not finalizing, then we need to keep the blobs for longer.
No, well, oh, I see it. Well, so like if you're in the middle of an inactivity leak, that probably makes sense. I mean, I think like I personally favor blobs being around for long enough, like a month, like at least a month or so, so that any like it's longer than any realistic inactivity leak that would happen. But no, there's different approaches.
Just on the setup, was there like a consideration, or is it even possible, or what's the problem with actually making that like a separate system? It reminds me a bit to like Swarm as it was integrated into Ethereum nodes. Like, wouldn't it be possible with pre-compiles and like the right new EVM opcodes to actually make that an independent system? Or
so the reason why we need like data availability sampling in consensus and why it's like so different from IPFS and everything out there is because we want to actually have consensus on the fact that the data is available, right? Like like IPFS does not provide that, right? And there's ways to like upload files so that some people think it's available and other people think it's not available. And for like regular file publishing, that's fine, because if a file is half available, you just publish it again. But for rollups, like you need like exact like global agreement on which data was published on time and which data was not published on time, because the rollups, like in order to figure out the current state of a rollup, you need to figure out like which data blobs to include and which ones to skip over. Yes. And tightly coupled with the chain.
Okay, next question here.
Hi, for the sort of data blob storing period, are there any thoughts about like challenges for validators that kind of keep that data, or is that purely altruistic behavior?
There have been proof of custody designs that we've worked on over the years. I think it's on the sort of rhetorical back burner because we just like know that these techniques exist, and like we know that when the time comes, we can probably just stick them in to get extra security.
Yeah, so I wanted to ask about the multidimensional fee market quickly. We talked about this excess data gas field. I was just wondering if the same would, like in an ideal world, if we hadn't already done EIP 1559, would the same construction be wanted for the like original kind of gas?
Yes.
Yeah, but this can't happen simply just. Could this happen?
EIP 1559 could be upgraded to that over time.
Okay, cool.
So I think there are even already thoughts in that direction. So I think over the medium term, we would want to. And one of the nice side benefits it would give us that it also makes other improvements to a 1559 like mechanism easier. Like for example, like a time-based instead of a block-based kind of throughput targeting. So yeah, we would probably want to homogenize this over time.
Yep. So I could be wrong on one of these assumptions, but my understanding is that proposer-builder separation was motivated largely by the centralizing effects of MEV and us wanting to keep the proposer set decentralized. But then kind of later with these designs like full sharding, we realized that we could utilize the builders as kind of with extra hardware requirements because they'd be incentivized with the MEV that they're extracting to have these nodes. But then there's also research into completely mitigating MEV. Okay, so maybe that's the wrong assumption.
Well, okay, there's multiple strands of research, and some of them are definitely sort of covering for each other in case the other fails, and some of them are complementary, right? So there's PBS, which allows proposers and validators to be more decentralized, but at the cost of kind of shifting that centralization to builders. There's a separate strand of research on the topic of trying to make builders themselves decentralized internally. So like some kind of protocol would plug into the market and make bids instead of being a single actor. And then there was also research on making applications that are MEV minimized. So like all three of those exist.
Okay, I guess the question is just simply like if we mitigate or very minimize MEV, then how do we incentivize
It's just like
builders?
minimizing MEV doesn't mean MEV goes away. It just means we do as much as possible to reduce it, but there's no, again, like I think anyone that has thought about MEV for some time will come to the conclusion that it's just not possible to assume that there's not going to be an incentive to be a specialized actor. Like there's, even if all transactions are encrypted, there's always going to be some reason to be the first to touch this state. Like, you know,
Okay, so the idea is they'll still be incentivized to run these nodes.
Yes, there's always going to be, I think, a lot of money to be made by controlling a block. I don't think that if Ethereum is a platform with value flowing, essentially.
Right, and just to briefly mention, it's not just Danksharding, where basically a PBS-like architecture would help. So once we move with worker trees to a world where it's easier to run stateless nodes, then also with what PBS would get us would be that like normal validators would basically all of a sudden have like way lower storage requirements, and we don't get that if they still have to create blocks, because then they need the state. But if you only actually validate but you don't create your own blocks, you leave that to a specialized entity, then you can as a validator turn stateless, and that's kind of the one more of these benefits we would get out of this.
Wouldn't it make sense to like charge for sampling or something like that to like motivate people to have the data and be able to collect the charges?
I mean, I think that's definitely a possible construction. You could like see a way like where you have, a specialized sample provider and you pay them. I think like the downside is that it makes it much harder to run a node because now you need to somehow set up this payment infrastructure. So I think it's not ideal, but it's possible.
And next.
Hello. Will there be ways to for somebody who wants to make data available to provide a proof through a smart contract as well, which is independent of this call data layer 2s and so on, which is smart contract specific, like as a generic infrastructure for proving that data was available?
I mean, that's what this construction does.
Okay.
Like this is part of like there will be a type of transaction that is called with a KZG commitment and with the guarantee that this data is available.
And then also being does there need to be like a special opcodes in Solidity to run the proof then to check that it was actually provided, because that doesn't
data was like, if you get that commitment, it was provided.
Yes.
Full stop.
But if it's
there's no extra check necessary.
Yeah, that it was provided. But then if let's say somebody wants to have a check inside Solidity if the data was available.
But it's a parameter. It's just like you get this commitment and you know it's there. It's like extra data.
If you want to check that the data is available behind a commitment, you use a history proof to prove that that commitment was in a transaction in some case.
Okay.
Any other questions?
So one way to understand the data availability sampling network, can we basically interpret it as kind of like a dedicated IPFS, but with the samples that distribute in the network, and the validator sample it, but definitely IPFS has some...
IPFS is a very bad way to think about it, because what we're doing is not storage, it's proof that data was not withheld.
Yes, but I just like kind of like for the network perspective, like yeah, and I know IPFS is vulnerable to Sybil attack. Yeah. that's something that is going to be addressed.
I mean, I think, yeah, from the kind of network perspective of how the thing should be implemented, like this thing has much higher requirements in terms of Byzantine fault tolerance and in terms of real-time access and like real-time being able to change what you're accessing.
Yeah.
Those are probably the biggest differences in requirements.
Okay, great.
Next question. There.
Like, if you don't mind, have you enjoyed your stay in Colombia so far? Sorry.
Yeah, no, I have. It's been very fun. Thank you.
Next.
Thank you. Something I was thinking about is that if we assume that MEV exists and that people want to sandwich other people's transactions and stuff like this. So we have this proposer builder separation, which makes a lot of sense. And then once we have this, we kind of start to utilize it to do heavier work like Danksharding and things like this. One of the things I'd be concerned about is that presently we have the ability for users to just simply not run MEV and they just let the transactions come in as they will and they lose a bit of money, but they're kind of genuine people. I'd just be interested to make sure that we don't rule out this person and we don't kind of glue together the role of like making really specialized fancy sandwiching blocks and then also doing all of the Danksharding stuff. I think it'd be nice if we can make sure that we keep a space for the home user to continue to pack their own transactions and just be like, a nice guy. Or girl.
Yeah, no, well, no, this is actually one of those things that I think I wrote an ETH research post about last week, right? Like basically, like can we push the autonomy in choosing block contents back to the proposer, and like that's a spectrum that potentially could go all the way up to the proposer having an option to make everything. And then one of the conclusions there was that if we want to have that kind of proposer autonomy property, but also have the property of like potential low proposer requirements, we might need to have a third category of actor that does things that are kind of not MEV extraction that in basically the entire bundle of computationally expensive stuff. So like witness addition, state root calculation in the future, ZK snarking, and figuring out polynomial commitments and proofs and broadcasting and so forth.
I mean, I just want to comment. I think like people need to stop thinking of MEV only as a bad thing, because you think of sandwiching, and even without any front running, any sandwiching, we still have lots of MEV, and it's actually a necessary part of the system. Like someone needs to do the arbitrage on the exchanges, someone needs to do the liquidation, someone needs to submit the fraud proofs. All of these are MEV. So don't think like we're incentivizing a bad thing here. So it's a part of the systems we're building. Depends, but I mean, I would say, for example, you can eliminate the bad MEV using transaction encryption, for example, but you'll still have loads of MEV left. Like, yeah.
So I forgot what I was going to say. I think, well, basically, like we're relying on ethical builders. I think there's like all kinds of techniques that we're layering on top to limit the power that builders have to do like the really nasty things.
A question on the PBS. So here, so will we like sort of apply some slashing mechanism once we have a separation between the builders and the proposers, like sort of on different actions they probably have? Yeah.
So there are slashing mechanisms, like different slashing mechanisms at play, right? So like there's a slashing mechanism that slashes the proposer if they make two conflicting blocks. In some of these partial block auction protocols, we use eigenlayer, and that's like basically exposes the proposer to kind of extra slashing if they if they violate the rules of the partial block auction protocol. Builders can get slashed in some contexts. I mean, forget exactly which ones, but there's definitely a few cases. So yeah, there's definitely like different forms of slashing to make sure the different participants follow the rules of the protocol.
Yeah, thank you.
Next question.
Maybe last question, so we have time to get to 12:30 stuff.
Yeah. No question.
Okay.
Okay. Okay, I think you are good. Thank you for joining us with for this 2 hours and 30 minutes.
Yes, I think my part was in Chile. Everything
Right, continue press off on.
Okay.
Check.
Perfect. Yeah.
Testing, testing. Started.
Hey, test. Okay. Okay, before we start, this is going to be an hands-on workshop, so you're going to have a couple of exercises to do. You can already like take a picture of the QR code and clone the repo so that you will already have everything. Hey everyone, so welcome to this workshop on how to build secure contract using fuzzing. Before we start, just to get like the first one is using unit test, the second one is using manual review, and the two last techniques are using fully automated or semi-automated technique. I'm assuming everyone here is familiar with unit tests. You should use unit tests, and they are good usually to cover that the system is working as expected in the happy path. Something that we have learned over our audit and over the analysis that we have done is that there is no correlation between the quality and the quantity of the unit test and the likelihood of having high severity vulnerability. And this is, we actually have an academic paper on this where we have looked over like all the audits we have done, and this is a correlation that we have not found. And the reason why our intuition tells us that when you're going to write unit tests, you're going to try to cover happy path, things that are supposed to do in the correct execution, while vulnerability usually lies in the edge case, in the things that you have, and the tool is going to tell you there is this type of bug or not. For example, you might know Slither, which is our static analyzer for Solidity. This type of techniques might give you false warning, but they're also really powerful because they might catch, critical bugs. Oh, yeah. Okay. Okay, so for Slither, like the best technique is spend 1 hour, like the first time you try it. There is a triage mode, so once you have triage, like the result, they won't show up like in the next execution. And if it takes you like 1 hour, and at the end of the day, you might be able to catch critical vulnerability, I would say it's worth going through the false result. And like we have like a list of trophy for Slither that demonstrates that we have found a lot of like actual bugs using it. So yes, there is like a false positive pass for false alarm, but it's not going to take you so much time, and it's going to provide you value. For example, we have a GitHub action with Slither when you can connect it to GitHub. On every pull request commit, depending on how you are going to configure it, it's going to run to see if you are introducing new vulnerability.
Yeah, perhaps, sorry, perhaps next year we will do a Slither workshop on.
Yeah. And this is open source and it's free. Okay, the last technique that you can use is using semi-automated analysis. So these are going to be tools for which you are going to provide some information, for which you are going to have a human intervention to explain to the tool what you are looking for. And this is a bit more difficult to use because it requires like this interaction from the user. It's a technique we are going to see today with property-based testing with Echidna. So what is property-based testing? To understand how it works, I have to introduce fuzzing. So fuzzing is a standard program analysis technique that is used a lot in traditional security. The idea is basically you provide a random input to the program and you try to see what's going to happen. You try to stress this with random input. The most trivial fuzzer that you can write, you just go on your keyboard and you push random button and you see what's going to happen on your program. Again, it's well established in traditional security. We have a lot of tools, AFL, libfuzzer, gofuzz, and so on. However, most of the traditional fuzzer are going to look for memory corruption, for crash in the program. We don't have a lot of memory corruption on Solidity. There are some, but they are not that common. What we are going to try to look for is property of the system that can be broken. And this is why we call it property-based testing. Basically, the way it works is that the user is going to define invariants. The fuzzer is going to explore randomly the program and is going to try to see if the invariant hold or not. you can think of fuzzing really as like unit test on steroid, where with unit test you try one specific value with a program, while fuzzing is just going to try randomly a lot of different values. I've been talking a lot about invariant. So what an invariant? An invariant is something within your system that should always be true. It's something that should never be false, or that should never be not possible to check if it's actually holding. So I've talked also about Echidna. So Echidna is our fuzzer for smart contract. It's open source. We have been using it for like 4 or 5 years even now in all our audits. You can see a list of mature code base actually using and have integrated Echidna in their process. For Echidna, we are focusing on the ease of use. So the invariants are going to be described in Solidity. We have a GitHub action similar to Slither. And we support all the compilation framework. If you use Foundry, Ardart, Brownie, Truffle, whatever, we are going to support it because we are using it in every of our audit, and every now and then someone comes with a new compilation framework. Okay, I was talking about invariant. So let's say you have a token. You have an ERC20 token. It has a balance. You can transfer token. What would be an invariant? An invariant could be that if you have a total supply, no user in the system should have more tokens than the total supply, right? If you have 10 million of token, if a user of 20 million, yeah, something is wrong.
Yes.
Okay, so the question was, what are the benefits of using Echidna over Foundry? So first, I think Echidna has more features than Foundry at the moment. They were developing Foundry for like 6 months. We have been using Echidna in like 4 years. We support any compilation framework. So let's say you are using Ardart because you want to do integration test and you need some complex setup using like TypeScript or whatever. If you move to Foundry, you're going to have issue because it's more difficult to create this type of test. So you end up in a situation where you need to have a setup with 2 different compilation framework. If you use some advanced options, then you have to need to have like both advanced options in both compilation framework if they support it. And it's a lot of like maintenance. Here we are like agnostic to the compilation framework in that sense. We have, we're going to talk about that later. We also have like a couple of advanced features that the other fuzzers don't have. For example, something that you can do with Echidna is that instead of trying to find invariants that are broken, you can look for functions that consume most of the gas. So you can let the fuzzer run and give you a summary of, okay, I can run this function with this parameter and it's going to output this amount of gas. And if you are looking for this type of things, it's really nice.
Hey there, Brock from Foundry here. I'm curious, how do you go about benchmarking a fuzzer, right? So how do you, because it's something like, for us, it's just a black box.
Yeah.
And yeah.
Okay, that's a really good question. And even in like traditional fuzzing, like if you go like in the literature of how fuzzer are benchmarked, I would say that most of the benchmark are poor. Or one of the issues is that when someone does a benchmark to benchmark their own tool, there's a bias, right? So we have benchmark, we have our own benchmark to try to see like in our past audit and everything how it works and everything. But obviously we have a bias. Like it works well for us because we are building the tool on our example. So I would say like the best place to have like a good benchmark for fuzzing should not come from tool developer. That's my
yeah. It's also an open question. What is your benchmarking? Like, if you're saying, well, this is faster than this other thing, but it could be executing just always the same thing. Like calling a constant function over and over again is going to be faster than calling some deep part in the code. On top of that, you have like bugs. What about like finding bugs? How much bugs you found? And there are a couple of academic papers saying that some people like to compare this, but you have like a plot saying how many bugs you found. And let's say that one fuzzer is better than the other, but you don't know if in the next hour you will have a peak saying, well, this found a lot of things. So there are other things that you can do. So you can use coverage, but also coverage is not going to give you like it's not going to be the ultimate answer. So it's still a debate how long you should run a fuzzer for a benchmark or even for testing something. It's also a debate what we should use for benchmarking. Should we use like complex DeFi applications? But how many of them we have? Like 10 or 20? We don't have thousands of different DeFi. So we definitely are interested in a deeper discussion on how to have a good benchmark set for tooling.
And we have the same problem, for example, with Flitter, where how do we benchmark that? Our static analyzer provide good results? And it's tough. We usually tend to have a practical approach in the sense that if the tool provide value during our audit, if it helps us, to find bugs and make us faster, that's good enough for us.
Yeah, and at the end of the day, also depends on the invariants. If the developers don't know how to write good invariants, then no tool is going to provide some magic value. So it's tough. Okay, and I'm happy to discuss with the Foundry team or any other team doing fuzzing. We'll be here today. So please let us know.
Okay, my other question is regarding like the tool is only for fuzzing or it support like symbolic execution or something like that.
So yeah, you want to?
Yeah, it's only for fuzzing. We have another tool for symbolic execution, which is called Manticore. However, and something actually we're going to discuss later, I think in practice, any formal based method approach is going to have a lower return on investment at further. If you have 2 weeks, 3 weeks to work on a project, and you want to invest some resource to increase your confidence in the project, fuzzing is the best solution.
Yes, and also we found that Echidna is a tool that works with our static analyzers leader that gets value. So you have in some cases like let's say that you have a test that says if x equal to some value. Some traditional fuzzer techniques have hard time to deal with this, but what we do is constant mining. So we scan all your code, look for these magic values, and we replay these magic values and some mutation of that from time to time. So our fuzzer should be able to get inside this. If you have a test case that is not working, please let us know and we can try to see it. But in practice, it seems like some of the typical use cases for symbolic execution in which you have constant magic values to look for, they can be replaced by constant mining extraction.
How many of you have issued to install Echidna to run like the exercise? How many of you have issue like installing Echidna or opening like the different exercise?
Okay. No, you have to open your terminal and Echidna will deploy so you need to install the tool, and when you put like Echidna test some contract, it will compile it running inside the simulated blockchain and give you the answer. So you don't need to connect into something. So yeah, go into the repository, and it says like so yeah, this is like the original one, but if you go into the Devcon branch, yeah, that is one thing. Yeah, sorry. Yeah, so it has more specific. Yeah, so over there you said like if you're using Mac, you can do that, or you can download. Okay, yeah. Okay, yeah. So wanted to highlight one little feature that we are testing on Echidna that is also using fuzzing, but instead of testing a property, we're doing minimization or maximization of some value. So this is a new thing that we are testing. It is not property-based testing, but it's something that we are trying to push. So if you want to know if a user it's capable of extracting tokens from your system without you to realize, you can use that feature. Just saying, hey Echidna, can you maximize this balance of this account? So it will try to generate you the maximum sequence. So it's a little bit outside this, but it's something that we wanted to mention.
In 5 minutes, we will show the solution. Did anyone already solve it? So for the people that are trying to install Echidna with Bro install, the Wi-Fi is a bit slow. Hopefully it's going to get better over time.
Anyone else needs help with the installation? Okay, you can continue.
Okay, I'm going to show the solution of the first exercise. Hopefully, in a few minutes, everyone will have Echidna installed, but yeah, we'll see. Okay, so our target here is a token. It has a transfer function, like a classic transfer function. It inherits from a posable contract, which is like a basic posable system. And what we want to try to do here is to create the invariants, such as no user should have a balance above the total supply. To test the token, the way we are going to do it is that we are going to inherit the token or target. We are going to create the contract test token. We are going to initialize the balance of the caller, so of the first user, to 10,000. And this is initialization. So you are creating a token. There is 10,000 in one address. And now the invariant is simply that no user, so the user Echidna caller should not have more than 10,000 token. Again, you deploy a token, 10,000 token to one user. This user should never have like 20,000 token, right? And if you run this with Echidna, Echidna is going to tell you that this invariant, this property on total supply was broken, it failed. And it's going to tell you how. And the answer is that it just calls the function transfer with a destination address 0 and 10,093 token. So what happened here? This was compiled with Solidity 0.7, so there is no overflow and underflow protection. So there is an underflow problem here where if you try to send more tokens than you have in your balance, the balance is going to underflow and you have a really large balance. Something which is interesting here is that we define the invariance, without looking at the code, without looking at the function. We were not looking, is there any issue in the transfer function? We just define an invariant. And by doing so, we can realize that there is a bug in the transfer function. So this is kind of a nice way of trying to find bugs because you don't look at the individual function necessarily. You can just define invariant, and the further is going to try to break the invariant for you. Does that make sense? Any question? Yeah. Okay. So the question is, does it execute a specific function, or how does it know which function to call? The answer is that it's going to call everything. So in this token, if you look at like the whole source code, you have a transfer function, pausable function, and some additional functions. So the further is just going to call everything, and everything external or public, like everything that a user can call. Okay, the question is, if you have a very large token or a very large contract, you have a lot of function. So here you can take different approach. Either you want Echidna to call everything and you just do nothing and you let Echidna run, which might work, it depends on what it is. If you know that some functions are more important and you want to target, you can change in the configuration file of Echidna and tell him call only this function or don't call this function. So it depends what you are trying to look. If you want to increase your confidence, you should call everything. If you think they might have an issue in a specific function and you want to focus on that, you can blacklist or whitelist. Okay, so the question is, can you define the order of call? You can define the order of the initialization, but not after that. I think there was another question. No, okay. Yeah. Okay. Okay. So the question is, can you have like a better log? Because obviously this is like a simple example. And when you do random, exploration, you might call a lot of functions that are not necessary for what you are trying to call, right? And the answer is yes. So Echidna does what we call shrinking, where once it found a way to break the invariant, it's going to try to reduce the trace. So it's going to continue to fuzz more or less on the same, iteration, and trying to reduce like the size of the trace. Okay, then we have the second exercise. Same instruction. So on the same repo, just call exercise 2. It's on the same target, so you're going to try to have an invariant on the same token. The first invariant was that no user should have a balance above total supply. Here, as we kind of hinted before, this is a pausable system. So it's a system where the owner can pause or unpause the system. And what we want to verify, the invariant we want to have, is that if there is no owner and the system is paused, can someone unpause the system? And this is what we're going to try. And yeah, let's take 10 minutes for this one. Okay, I'm going to show the solution for the second one. So it's the same target that for the first exercise, but here we are going to focus on the contracts that were inherited by the token. You have two contracts, sorry, ownership and posable. And here you have a system where you have an owner and you can pause or resume the contract. And what we want to check is that if we drop the ownership and we pause the system, is it possible to unpause it? So here we have a bit of initialization to do, right? Because we want to drop the ownership and we want to pause the system. We are doing this in the constructor. So we are calling pause and owner. From now on, the system, as the contract is deployed, it's paused, there is no owner. The invariant is then just if the variable that tracks the pausable state of the system is true. And this should hold, right? You pause, no ownership, it should be always paused. And Echidna tells us that it actually failed. And the reason for that, so this is kind of like an old bug that were really frequent and common in all versions of Solidity. There was no constructor keyword, and the way you were doing the constructor is that you needed to have the function name, which was a match with the contract name. And here you have the contract ownership and a function owner. And because of that, the function owner is a public function, and anyone can call it and become the owner. This does not work anymore with more modern version of Solidity, but it's the type of bug that we are finding a bit more, a bit too much in the past. Something which is interesting again is that we did not look at the ownership contract. We did not look like at the implementation itself. We just defined an invariant, and we let the one of the further one, and it found the invariant for us. So now brings the question on how to define invariant. Okay. Okay. So the question is defining invariant part of the auditor work? Yes, like we are using Echidna in our audit, and during our audit, we are going to define invariant. And something we are going to do is that we are going to discuss with the developer because the developer know better than us what the system is supposed to do. So we are going to have this collaboration with them to understand what the system is supposed to do and to define this invariant. Now to the question how to define invariants. Because, like, if you have bad invariants, it doesn't matter what you are doing. If you are using fuzzer, if you are using like formal method, if your invariant are not good, you're just going to check for something that, doesn't matter. The best approach to write invariants is not to start with a tool. It's not to start with, writing down Solidity invariant. It's to start with English. Open a file, a markdown file, or whatever format you like, and write in English what the system is supposed to do. Start simple. Start with invariants that are true. Start with things that are not broken. Once you have 5 or 10 simple invariants, write them in Solidity and run the fuzzer on top of them. If the invariants are all holding, then you can go back to thinking about the invariant of the system and go more deeper into the invariant themselves. If something is broken, then look if the invariant is incorrect or if there is an actual bug. And iterate, go over
Yeah, in our experience when we work with clients, when we ask them to do step one and define the invariants, they are actually they realize about bugs. So it is already a very good thing to start thinking into that, even if if you're not testing. Yeah. Yeah.
But what about testing on in the text? What is the function which breaks very slab? It's real clock was founded by Blob. And still, can I make a payment for and use this variant testing?
Okay. Okay. So if I understand correctly, the question is that can we connect this to mainnet?
Yes, mainnet or some how maybe we can use it with other contracts.
Okay. Okay. Okay, how to use it with other contract. So you can just in the constructor deploy the contract, or something that we are not going to cover here, but we have a tool which is called Echidna, which is basically going to take your unit test, take like your suite, and we play them in Echidna. So for example, if you have like a complex integration with like, you are deploying in your unit test 10 different contracts, you are deploying like a mock of Uniswap or whatever you need, and you can replay this in Echidna so that everything is going to be set up.
Yes, yes. I think there is a little bit something else there that you want to. What if you want to define an invariant on a Uniswap contract, right? That you are using, that your contract is using. So you will need to know how Uniswap works in order to put it in your invariant. Like if I'm swapping something, then I'm getting something else, right? And in that case, you need to realize that it's difficult to write invariants with other people code, right? Despite this is working and everyone is using it, but every time that you use a third-party contract, then you are importing some risk, and you need to completely understand the other contract in order to know what is going to the effect in your own contract.
I could ask an explanation. So what was the real case? Have a special type.
So the risk case was we have a special, I'm from Gearbox protocol and we work on composable leverage, and we have adapters because we just provide leverage for some other contracts. So when you combine Gearbox with Uniswap, you get immediately margin trading. And in this case, we have adapters, and these adapters incorrectly parse path to make check after Uniswap. However, they integrated and make code to existing Uniswap. And guy who were on Immunify problem, he write a small test, and this test show us that if you really add some additional part of call data, it could be interpreted incorrectly. So we have two different ones. Our system could be fooled, check not that balance which should be checked, and in this case it was a fault of the system and the funds could be drained. And in this case I think we could find some fuzzing testing to really provide any information, but this test should work with Uniswap because we behave in different way, and we shouldn't cover that because we run with mocks, and mocks of course was created with the same bug, so mocks was okay, but real implementation total different. And I definitely believe that fuzzing should found this mistakes.
Yeah, definitely. When you are creating a mock, you are assuming how everything works, and if your assumption is not precise enough, you won't be able to detect something. And we as an auditors, it's common that we have to audit contracts that will interact with other contracts. Let's say Compound. So when we go into Compound, we have all the documentation and says, well, Compound works like this or like that. When we look at the code and see some things that are not documented, and we go back into the developers and look, if your contract is doing this or that, it will revert, and you're not testing for that. So it's when you are using a third-party contract, you are importing the risk. So either you have really good tests, or you even make sure that you understand everything. Otherwise, it will be difficult to catch the bug.
But yeah, I think this type of bug can be found with fuzzing. The difficulty is going to find an initialization that makes sense and an invariant that makes sense. That's why we are kind of putting like the emphasis onto defining invariant, because this is like the key component of this technique.
Yeah. In terms of speed, is it okay to put all deployment script into constructor? Because of course, if you deploy such a huge system and you deploy some contracts from external repositories like Uniswap and so on, it requires time. And of course, when you want to test million operation, if you redeploy each time whole the system, it could require hours or days. I know.
Yeah. So when you use Echidna, you deploy it only once. And then when your test finish, it will go back to the state after the contract is deployed. There's no need to redeploy it. And that is why we ask the developer to have fixed amount of parameters in the deployment, right, on the constructor. Otherwise, we will know what we should deploy. Yeah, I think there is a question over there. So
I'm just wondering, as you once you've kind of defined your invariants, and I imagine you guys in your audits you run through these, and basically I'm trying to understand when you guys have confidence that yes, this is a good invariant from, and if there are any metrics that you guys use internally. Like I see it's outputting unique instructions and unique code hashes, those sorts of things that give you confidence in what you've done.
So in practice, you can look at the coverage, but usually coverage is not a good indicator. And in fairness, like, when we do that, we do this in a time box manner. So we have 2 or 3 weeks to do it, and we're going to do our best in 2 or 3 weeks. That's the best that we can do.
yeah, it's tough. There's no like silver bullet for this. When we do a report, we list the invariants that we test, so it's clear what we tested and everything else was not tested with tools. So we perhaps did manual review or use other techniques like Slither to check some other things. But yeah, unfortunately, there is no good way to define this. But perhaps I personally think that talking with the developer early on the invariants, it's a really good thing. It's usually the case that we think an invariant, let's say that some value cannot be 0, and we go into the client and says, is this an invariant? We don't know because we have not designed the system, and they don't know. And if they don't know, that's an issue, right? We should absolutely know what is the behavior of the system, and if we don't know if an invariant if something should be an invariant or not, then we should go back and rediscuss that.
And yeah, security in general is not binary. It's not, yes or no. It's really a matter of how much resource you want to put into it. And more resource you put, more confidence you will have.
Thanks. I have a question actually more related to the earlier question, which is a big class of bugs that's been occurring recently and for a while now are reentrancy bugs, right? How do you deal with finding violations of invariants that correspond to external contracts in that way?
Okay, so this is a really good question. And in my opinion, the best tool to find reentrancy is static analysis. So the question is more to find which technique you should apply for which problem. And for things like reentrancy, Slither and static analysis is just going to be better. You can use further, you can create like reentrant callback and things like that. But in practice, static analysis is just going to outperform any further at this work. That's why like for any class of vulnerability, which is kind of a pattern base, you can use static analysis and it's going to be better in my opinion.
And one more question, what's your addition? For example, we have a complex system and we want to make a classical fuzzing with Echidna. And it seems that to really cover many cases, it requires a lot of computational power. So maybe can you advise some cloud provider how to run it maybe for a week with very powerful computer to get something achievable? Because of course, these pretty simple contracts could be found on my MacBook, but if you go a little bit further, many contracts, many setups, maybe it requires more computational power.
So, Gustavo, do you want to talk about Echidna Parade? So the question was, if you want to run Echidna on the cloud or on a lot of, a large like system, how can you do it?
Yeah. So the first thing that you should know is that if you have a very large contract, it can take some amount of memory. So first thing, get a good server with a good amount of memory and CPUs. So the second thing is we have a Python companion tool called Echidna Parade that will run Echidna in any number of concurrent instances. So you can run 10 at a time. But we are not only going to run it 10 at a time, but we are going to randomly shuffle parameters, because in some cases there are some issues that can be easily found with, let's say, 3 or 10 transactions, and some other issues are going to be more easily found with 200 transactions in a row, right? So what we do is we run the tool with different random parameters and in different, let's say, generations. So we run Echidna for an hour 10 times, then we save the corpus, and you can see all the code that was covered, and then we start again, but taking the output of the previous generation. So you iterate over and over again, so you can see how your code is explored, right? Or if there's some part of the code that is not explored with 10 different instances, you can go back and say, no, I need to change this because it doesn't depend on the actual execution. So we can give you the link for that. It's just a Python tool, so it's easy to use.
Yeah, it's also open source. Like everything we are doing is open source. Okay, so yeah, like it's really about spending time and thinking about our invariants. And start simple. Like if the first invariant that you are writing leads to a bugs, there is something wrong about your approach. You should not have like simple invariants that are going to block the system. So we'll start simple and iterate over them. Okay, to give you some example, let's say you have an arithmetic libraries. What invariant can you have? You can have commutative properties. A plus B is equal to B plus A. You can have identity. 1 multiplied by 2 should be true. Or inverse, if you add something by its opposite, it should be 0. This is not always true, right? But depending on what you are building, this might be like the type of property you are looking for. For token, we already talked about the first one. No user should have a balance above total supply. Let's say you want to look at the transfer function. And let's think, transfer function, what does it do? I'm transferring token to someone. So at the end, my balance should have decreased by the amount, and the receiver should have see its balance increase by the amount. And let's say you try to write something like that. What you might quickly realize is that what happens if the destination is myself. So if I transfer token to myself, my balance is not going to increase or decrease, right? Hopefully. So this is an example where you might try to define an invariant on transfer. It might seem simple. You might write like the thing in Solidity. And if you do that, Echidna is going to tell you that there is an edge case where if you transfer to yourself, like the invariant is going to be broken. And in this example, if you go through this, it's not the code which is bad, it's the invariant that was bad. So that's why having this iterative approach is really important, because sometimes you are going to make assumptions about your system and you might actually be wrong. And as the system gains in complexity, it's more and more likely that it's going to be more difficult to refine the invariants. Something else which is also important to consider is returning false or reverting. For example, an invariant you can have is that if you don't have enough funds, the transfer function should either revert or return false, depending on how you implemented the token. Once you have this list of invariants, usually you can split invariant into two categories: function level invariant, system level invariant. Function level invariant are usually stateless. They are things that you can just look at a specific function and try to see if it holds. So arithmetic invariants I mentioned are stateless and are function level invariants. Here you can craft simple scenario just by calling the specific function. Then you have system level invariant. System level invariants are usually more complex, but they are also more powerful. And here you are stateful. You are going to change the state of the contract, and you are going to try to see if the invariant holds no matter the state. And here it's why it's important that Echidna is calling all the different functions, because it's actually what you want to try. The balance being below or equal to the total supply is an example of a system level invariant. For function level invariants, one thing that you can use is a different mode on Echidna. Instead of calling Echidna underscore something, we support assertion. So you can just create function, put assertion, and try to see if it holds. For system level invariant, as we kind of already discussed, it might be more complex depending on the initialization of your system. If it's a simple initialization, you might be able to do everything in the constructor. If the constructor is too large for the bytecode size or for whatever reason, you might have to split it, and here is where you can use Echidna. Echidna, sorry. Okay, yeah.
All right, so let's see this particular piece of code. Let's take half a minute to read it. It's basically a by function that will call an internal function valid by. So what we are going to do is we're going to think what are the type of invariants that we can have here, and what will they're going to test, and what type of guarantees we're going to get from this. So let's take a few seconds for this. Yes, so we have a question. Okay, so the question is testing timestamp dependent. So clearly not the case here. For timestamp dependent code, Echidna, when it runs, it automatically increase either the block number or the block timestamp inside some range, right? Because it happens that some code will fail when the timestamp is increased into a really, really large number. But yeah, 100 years or like the end of the universe. So we don't care if the smart contract has a bug that can only be triggered in the end of the universe. Will be the least of our problems. All right. So yeah, any idea what are the type of things that we can test here? Yes.
The first one, we can understand that how many tokens we can get as a result follows our expectation when we're sending message value, because as I can see, it's a hard-coded rate is around 10. So basically, it's a pretty simple formula. We can change different value we put into the function. We have totally prediction how much we can get, and then we can try to verify that it works.
Yes, exactly. So the property is related with the amount that we can get given the number of way that is sent. So we can. So the first thing is this code will depend on the state. We don't have the mint function, so we don't know what is inside. However, we have the valid by function that is actually abstracting the thing that we want to test. So we will start with valid by, which is a pure stateless function. Yes, so we were thinking about invariants here related with the amount that we can get. So this is a very simple, without going into specific, this is a very simple invariant. If the weight sign is 0, then the user should receive no tokens at all, right? So it's even simpler than thinking how much a user should receive, but it's a concrete case and it's kind of a corner case, so it can be important to test. All right, so how we can test this? So there are a couple of ways to test it. This is one. So we can write a function that will take one parameter. So I will put any number there. However, we're going to restrict the number, the input of this function to be non-zero. Then we're going to execute valid by, and then we want to know if Echidna can reach the statement after that, because valid by will revert if the inputs are not the one expected. So we want to know if we can get tokens despite sending no value, right? And so perhaps you're wondering, what if this amount is zero? Then clearly this code will not do anything interesting, which is going to revert. When you're writing tests, you need to, so you can put any amount of requires or preconditions, or people usually call it. However, if you put if the preconditions are too restrictive and your function reverts most of the time, it means like you're not going to get value from the execution. So every execution reverted in a test, in an invariant, let's say, that every case that you don't use, it's going to be an execution that you waste. So in this case, you only waste one execution in a range of, in the full range of uints, 256. So it's not a big deal. But if you put a lot of requires that only a very small amount of values will satisfy, and it will be difficult to get randomly, or even with the techniques that we use, you will need a slightly different approach. But yeah, we will then go later into that. So any questions? Yes.
Yeah, so as you mentioned, in this case, that we are basically sacrificing only one case, which is when it's zero. But is it going to run over the whole range of UN 256? Because that's a really large range, and it doesn't make sense to test all of that in some cases.
Yeah, exactly. So it won't. There is no tool in the world that can run for all the range. It is always either symbolic. I mean, you can do it symbolically, but it's not going to test all the values. It's another thing. And fuzzing techniques are going to sample, let's say, randomly from the input, or with helps, right? It's in the case of Echidna, since we are going to compile this code and it will run through our static analyzer, we will detect some interesting values. In this case, 10, for instance. 10 is an interesting value there. It's a constant, and it's going to be used somewhere. So definitely we want to test with that constant. Okay, so let's see what happens if you run. So this is so Echidna will run a number of transactions. It will eventually detect that a certain free token has an assertion failure. However, this is going to be in the context of 100 of transactions, random transactions that perhaps will do something that is completely unrelated. But what we'll do is input minimization. Input minimization is a very old technique referred to testing, in which you have a list of bytes that affects a bug. You want to remove that bytes one by one, or in some random way, in order to get a list of bytes that will still trigger the bug, but is going to be minimal, or either a local or a global minimal, depending on the type of tool that you use. So in this case, we can Echidna will try to minimize any parameter. Here we have only one parameter, and the parameter is actually is actually going to be useful triggering the bug. If we have more parameters, they are going to be minimized towards 0. So if you have uints, then it will be reduced until 0. So 0 is the simplest value. This is arbitrary defined on the code. You can change it if you want. But in this case, the parameter cannot be 0, because if it's 0, the test will pass, right? So in this case, the minimal amount is 1. It's not guaranteed that you will always get the smallest set list of transactions to trigger. This is an NP complete problem. It cannot be solved on linear time, so it's all going to be always a sample. But in practice, even randomly sampling, removing transactions, or reducing the complexity of each value will give you good answers. All right. So a little bit about Echidna APIs.
Wait,
Yeah,
maybe
sorry.
maybe we can
Yeah.
just explain.
Yeah.
Just explain why it's happening.
Yeah. Yeah. Sorry.
Yeah. So the issue here is that if you send one desired token, what's going to happen is that you do 1 divided by 10, and 1 divided by 10 is 0, because you are rounding down, and as a result, the required amount to be sent is 0. So if you ask any number of tokens below 10, you are going to get them for free. And this is again an example where we define an invariant. We don't actually look at the formula. We are not looking at how this formula works. We just define an invariant that if you don't send Ether, you should receive no token. And by doing that, Echidna can find arithmetic issue. And we're actually heavily using Echidna for rounding, for mistake in the formula and so on.
Yeah. So. Yeah.
I get that this function is for testing purposes, but in a real situation, wait sent is not part of the signature of the function, right? You read that from the message.
Yeah. This could be like deeper into the code, right?
Right. So how do you do in that case? You read that into the asserting function. How you do that?
So yeah. So this, if I understand it correctly, so this could be an internal part, and you can have like a lot of code that gets the value from the message value and then do something else.
You can do that.
Yeah, I mean, this depends on your code. Here we are testing an internal function, right? Using some defined.
Yeah, and if it was using message.value, Echidna can also find message.value.
Yeah, exactly. So properties can also take value. So, and if you have a constant in your code saying message value should be 42, it will use that constant eventually. So you should be able to hit that particular case, given the fact that this is random sampling, of course.
But can you, moving back to the previous slide, to the function, what I'm really wondering, because we talk about this error, however, tokens less than is so way less than it's so small amount, and the same problem which could be here, it's overflow if I provide a huge amount of ease, because we have a multiplication to decimals, it could be done. On the other side, we all of us know that the quantity of s is limited. You can't even take a flash loan and get more ease than it produces. So what is the best practice? Follow this formal execution when you write fuzzing test, or take some real examples as limitations, as there is no much Ethereum as it exists at the moment, and we know it's a deflation, so we can simply assume that in the future nobody could take so much to get overflow here.
Yeah, exactly. So yeah, this is an interesting question, and it goes into the fact that what are your assumptions on the test, right? If your assumptions are like, I have this token with this limited supply that should never go over something, then you can just say, I require that the value sent cannot be more than the total supply of something, right? But in the case of Ether, is a little bit more tricky, and in fact, in Echidna, what we do is we have externally owned accounts that are simulated. We load it with Ether at every transaction, because you can have a very large amount of Ether. You can take a flash loan. You probably cannot have enough Ether to overflow you into 256, because that will be a real issue for the AVM in itself. But we can define in the Echidna config which is the maximum amount of value that we send per transaction, right? So if you put like, I don't care if the attacker has more than 10,000 Ether, because that will mean like they can do other things, then Echidna will happily take that limit and will never put something more. However, it's still the case that over several number of transactions, the accumulated number of Ether can go over that barrier. So you should be careful with that.
And there is also an approach that you can take here. So basically, you are building an invariant, and the invariant has a threshold, as like a value.
A question?
Yeah. So either you start where the invariant has really limited threshold, like really restrained one, and you try to see if it holds. If it's breaking with like with 1 Ether, okay, it's already breaking, so you can continue like this. If it's not breaking, then you can increase the threshold from time to time. Or you can take the opposite approach. You define an invariant where the threshold is really large, it's breaking because it's really large, and then you decrease the threshold. So either you start really limited, and depending on the result, you remove the limitation, or you start without limitation and you reduce up to the point where you have kind of like a value for which you feel comfortable with.
Yeah, and that is also related with the fact that, do we want to have false positives or false negatives? What is the risk? If we start with very large values, we could have false positives, and if we start with very small values, we can have false negatives. But which are the ones that are going to cause you more trouble? That is something to think about it, because if you miss one false positive, your protocol can be destroyed, and if you miss one false negative, then it could be okay. All right.
Hey there. In terms of fuzzing mutation, do you do any clever things like, say this function has a constant of 10, so would you then see the constants in the function and use that as input?
Yeah, we will use the constant from the function, and we will fuzz around the constant also. Like if you see 10, we are going to use 10, we are going to use 9, 11, around.
Yes, there are some techniques. I can show you a little bit after a few lines of the code of Echidna that shows all the mutations. We have interesting mutations on list of transactions in which we shuffle. We do like splice as well. So we take a list of interesting transaction and another one, and we splice it in a random position. So there are a couple of fun things to look at. But yeah, I think we should move on a little bit. All right. So as I was saying, we have this failing. Even if you don't understand what is the failure, well, that is a different beast. Sometimes you put your invariant, and your invariant fails, and then you start the journey to understand why it fails. So we are not going to talk about that. Some people like to rerun the failure into a unit test to make sure step by step what is going on. But yeah, that's a completely different type of beast that is related with what happened after and how we can fix the issue. All right, so a little bit about Echidna APIs. This is a topic that it's still an open debate in some cases. So what are the best way to test to create properties? So Echidna supports a couple different ones. It supports Boolean properties, in which a function is executed, and then it should return a Boolean true or false. And if the function reverts for any reason, that is the same as returning false, right? So if we go back a little bit, we can see over there error unrecognized opcode that is related with the assertion failure. That is how old version of Solidity used to have these assertion failures. But if you use Boolean, it will just say return false, right? So you know exactly how the property failed. Or it could be a revert. So you say over there, you see over there, it reverts. Okay, so either you do Boolean properties, which are the classic way to define invariants, and these come from some very old techniques, in particular quick check, which is a property-based testing tool for Haskell and a couple of other languages, which was an inspiration for this. Then you have assertion failure. So every time you see, every time the assertion is called with false, that will fail. However, if in the context of your function you see a revert, that will not make the function, the property fail. Here we can see that if valid byte reverts, then this Echidna will not report that because we are using assertion mode. Right. So you should be careful if you are using, if you care about reverts, you should have to either use the type of the Boolean type, or what you can do is, if you care about reverts in valid by, and if it's an external function, you can do a try and catch, and you can check which type of revert, and you can even fail in some type of reverts and not in other, because you want the user to get a good message of revert, and perhaps other type of reverts you don't you want to know. So and finally we have the DAP and Foundry API, in which you will have a function that if it reverts, it's going to fail, and otherwise it's not. And I hope the Foundry team agree with us, and it's is correctly implemented. All right, so there is testing modes in our repository, so we can you can go there, and it explains a little bit more. This is very high level overview. So yeah. So yeah, Echidna something return Boolean. It's easy to define. No side effects. That is so interesting. When you use Boolean properties, all the side effects will be reverted before the execution of the actual invariant, right? But if you're using assert, the side effects, so everything you change in the blockchain will remain. So this can be really useful for testing some complex code. But yeah, we're not going to. Yeah, assertion can be simple to define, and it will also be easy to see on the code coverage if it's not covered or not. However, some code, especially some old piece of Solidity code, it's going to have assertion as required, and that is a really bad thing. You should not be doing it. Use require if you want to actually have a precondition in your code, and use assertion for testing. Okay. Yeah. And finally, we have the Foundry and DAP compatibility. The only thing, well, the thing that we don't support is pranks. So we don't like to prank people. So we don't support pranks. However, we support some of the HAVM. Yeah, the HAVM, the original ones, cheat codes. You should be careful using it. We know that there are some catch with that, especially related with what the Solidity compiler expects and what you're doing in your transaction. So please be careful, because you could have some issues. So we rarely use cheat codes. We try to keep our code as close as the Solidity possible, so you can easily port it to another tool. There's little Echidna specific, but yeah, we are also open to discussion. If the community agrees that we need a specific cheat code, or we need to avoid some specific cheat code, then we are open to discuss it. All right. So exercise 4, we're going to deal with one of the exercise for damn vulnerable DeFi. So how many of you know this amazing CTF? Yeah, sorry.
But yeah, we can skip it.
Yeah, we can skip it. This is the
So this exercise was exactly the same as the first one, but instead of using function echidna underscore, we were using assertion.
Yeah.
So it's exactly the same invariant, exactly the same setup, but with a different API, just as an example.
Yeah, so we will go into a more interesting example. But before that, there is something that you will need, which is called the multi-ABI mode. So usually testing tools take a specific contract as your main contract to interact. So in the default mode, Echidna will only target a specific contract that you can put in on your command line, or if you have only one contract, you will use the first one, right? But there is something called multi-ABI that would call every contract that is deployed after the constructor that you have ABI, right? So if you deploy something in bytecode directly and you don't have ABI, Echidna won't be able to call it because it doesn't know what is there. But if you deployed a couple of tokens and several contracts and you use multi-ABI, Echidna will call any function in any deploy contract after the end of the constructor. So we will need this in order to deal with the next example, because sometimes the bug that you want to detect, it doesn't depend on the state of one contract. It depends on the state of many contracts. And in that case, you can be surprised by the fact that changing the state in another contract can break your property, and definitely we want to avoid that. Okay, so again, how many of you know about them vulnerable DeFi? Okay, a good number. And did you actually? Well, these are the first exercise, the first two. So I hope that people know. So if you know this how to solve it, you should. It's going to be even easier for you. What we're going to do is we're going to take a look of this example. So yeah, I assume that you already have the code. So it's the exercise, the naive receiver one. So what we want to do is we want to be able to drain the funds in flash loan receiver, right?
Yeah, just to give like a bit of description of the challenge. Here you have two contracts. You have the naive receiver lender pool, which basically
yeah, it's over there.
I can allow you to take a flash loan for a fee, and you have a second contract, which is a user contract that is going to interact with the pool. And the contract is going to be, the user contract is going to be deployed with some funds inside, and the goal is going to try to see if it's possible for this specific contract from the user to be drained.
Exactly. So what we want you to do is we want you to review the exercise. If you have already did it, it requires you to send some number of transactions. So in this case, we are going to prepare everything for Echidna to rediscover this without telling it how it can be solved. So we will need two things. We will need to initialize the code to have to match what the initialization is actually showing us. Let's see. Okay, so this is the flash loan, the part of the flash loan. So the interesting part about this is we don't have to care about specific details in the code. We want to give Echidna the same scenario that we have on the actual challenge, and we want to know if it can actually find a way to drain the contract. So yeah, we can see how the receive iter function works here. But yeah, the interesting part perhaps is the initialization. What we are going to do is we are going to deploy in the constructor of our test. We're going to deploy the contracts that we have here and prepare everything, and then we're going to use a suitable invariant, which should be really simple. You don't have to overthink, and we want you to run Echidna with that in order to see if it can drain the contract with a, of course, with a suitable invariant. So yeah, we will take
10 minutes, I think.
Yeah,
We're running out of time.
yeah, we are running out of time, but let's take 10 minutes.
So the first step is really like, this is a initialization from the test case of the contract. The first step is really just to replay this into a Solidity constructor and then to write the invariant.
Yeah, so happy to take questions or any technical issues.
That's the goal, actually. We are going to do exactly what he's doing here, but in Solidity.
Yes, there is an alternative way to do it, but the Solidity approach is easier to avoid. Because the other tool is called Echidna that can replay this in a simulated blockchain like an hash and then send it to the tool. So in that case, you don't need to replay it on Solidity manually, but you still need to know where is everything deployed, right? So if you want to interact with the pool, you need to know which is the address of the pool, and you can then Echidna cannot actually call the poll functions automatically because it has everything. But in this case, we're going to go into a simple route that is going to take us to rewrite. It's just a couple of.
And this kind of match what we are doing in audit. We might look at the existing unit tests to understand initialization, and we might translate them in Solidity if needed to then create the invariants.
So yeah, the previous exercises are on the easy side. This is a little bit more difficult, but still shouldn't require more than a few lines. So yeah, but please let us know if you need some hints. There are some hints in the in one of the branches, in the hint branch. But yeah.
Hey there. Hello.
Yeah, sorry.
No worries. Is there any thought or current support for mainnet forking or state forking of some sort?
Not yet.
Yes, so not yet. HAVM has support for that, but that will need us to put that requires to do like input output on transactions. So we need to check if that will impact on the actual performance on the code. So yeah, they will.
I have kind of high level question. So I'm trying to think about what the limitations are in terms of expressing properties as invariants, right? So for example, let's say we have a temporal property that we want to express, like we have a wallet contract and we want to be able to say that any user who deposits their money is eventually able to withdraw it. Is that just like a fundamental limitation of Echidna, or is there a way to kind of handle that?
If you can, so the notion of eventually, it's you need to have some definition on the blockchain, right? So eventually cannot mean like in 100 years, right? So if you define, say, I will only allow increment of time up to some limit, yes, you can call it as a bounded version of that property, but you cannot use it as a theoretical thing, like, I have a state which I don't know what it is, and then I will transition to another state which I don't know what it is, and in that case you will need to know if the original state was actually possible and things like that. So Echidna works on concrete states. So you always have concrete state, and you need to put like boundaries on the things that you can do. So if you say a user should eventually receive this amount, and eventually means like in a number of transactions and in a number of blocks or timestamp, then yes. Otherwise, it's more like a theoretical proof that you're doing, and you probably need another type of tool.
Yeah, I guess I'm curious, even if you took like the bounded case, because that's fair that you're dealing with like concrete traces here. It seems like that's not, or it's not intuitive to me anyway, how you would express that as like one of these invariants.
So you will do something like this. You will put a function that says, and you will need a state to track down, like you do a deposit, and you will need a user to eventually receive something, right? So you will need to have a state that tracks deposit, like a mapping, right? And you have a function that is your invariant. So if and then you receive the address of a user, and you check in the mapping if the time between the last deposit is in this range, then you are going to check something. And if the time in this other range, you're going to check something else. So it will be like randomly checking in transactions, and with that you will be able to cover, given the fact that you're going to generate enough transactions and enough timestamps, right?
I see. So it seems like the answer is it's capable of doing it, but it requires some like kind of manual adjustment of the code almost to add state.
So yeah, so if the property that you are testing requires to add state, yes, you will need to add whatever state is needed. It won't be able to track state outside, right? The only thing that will be tracked outside is the increment between the different blocks, for instance. So that will be tracked outside, and Echidna will show you from in between this transaction and this transaction, I have 10 blocks. That will be tracked outside. But everything else, if you need to do a mapping between users and the time between certain operation, you will need to keep that in a different in Solidity in a different variable.
I see. Great. Thank you.
All right. So we have some other questions.
Hi. Is there any feature that allow me to guide the fuser over the domain of values that I want to try?
So in order to guide the fuzzer into a particular state, the easiest way to do it is to add a small piece of code that will be auxiliary code in order to move the state from your contract into something else. Like for instance, if you have a contract, the protocol that requires a deposit with a particular property, let's say that you have 3 parameters and you need a deposit that has these 3 parameters in the same number or in numbers in which are difficult to find, you can add this piece of code. But it's important to let Echidna to explore freely at the same time that you are adding information. So it's actually important to know that as an auditor or as a developer, you are adding information into it, not just using it as a black box, right? So every state transition that is non-trivial to find or is really, really important, you can add it and make sure that it can eventually execute it, because it's going to be another transaction to execute. But at the same time, you want to allow the tool to explore things that you don't expect. Because if you just restrict, says, I only expect users to do this type of deposits, then you can be surprised later, because there is a way to break your property using things that you don't expect.
Great, thanks.
And it comes down to the previous question, where either you start with a lot of requirement and a lot of restriction in what you are trying to explore, and if it holds, you are going to remove some of the restriction, or you start the opposite direction. You don't have any restriction, and you go more and more restricted.
other ones. So,
yeah, there's only one okay to it.
Yeah. So yeah, it's but this is yeah. Yeah, you or you want to go into the okay. Yeah, it makes sense. I saw some people solving the first okay. So did anyone manage to at least still start to create the constructor or even run it to have some invariant or even think about the invariant that you need? So in a couple of minutes we'll go over the conclusions and we'll show the solution. But yeah, happy to take any additional questions.
Just from an implementation side, I'm curious what actual like virtual machine do you use to deploy and execute contracts?
So we use HAVM, which is the virtual machine written in Haskell. I know that it's in the process of improving and rewriting, so it was moved from the DApp tool into the Ethereum repository, so we are eager to test new features. But yeah, if you use the Tino companion tool to deploy a contract, it's going to use Ganache, and it will serialize into a JSON file, and you can then load it into that. Okay. Do we go? Yeah. Do we go into the solution?
Yeah.
Okay. Yeah, we're going to quickly go over the solution so we can have a couple of minutes for this. So the solution requires first to have a contract with enough amount of Ether to match what is deployed. And then you can see here we deployed all the contracts that we need and send the amount of Ether that every contract needs. And then what we're going to use, a very simple property that is going to say that the balance of the receiver is at least 10 Ether. So we don't actually need to follow exactly what the exercise says about draining completely the contract. If we have one transaction that allows you to reduce the balance of the receiver, then something is wrong, and definitely it will eventually be drained. So yeah. So quickly, if you run it, you will see something like this, in which the function has a parameter that is the borrower, and we can control this in order to reduce the amount of balance. All right. So yeah, you want to go into the conclusions?
Okay.
Yeah.
Yeah, we had a second exercise on the vulnerable DeFi, but we are running out of time. The idea was the same. We are defining initialization, which was a bit more complex. And if you go through this exercise with something a bit more specific, is that there is a callback from the contract to the caller. So in the Echidna test, you need to have like also the callback to implement the flash load. But yeah. Okay. Yeah, so this is something we kind of touched on a bit during our discussion. What about the other tools? So there are a couple of other further out there. There is DAP, Brownie, Foundry. At least this one are open source. This further might be a bit better for simple tests and for like, ease of use for like the first invariant because they are integrated within the compilation framework. But in the long run, they might not be as powerful as Echidna, simply because we have, used Echidna for a couple of years and we have tuned it in a way that it provides the best value that we can do. Oh, okay, it's finished. Okay, sorry. Yeah. Okay, so I hope you enjoyed the workshop. We have more exercise in building secure contract. Something that I would recommend for you is to try to write invariant, in your next project. And actually, who is going to try Echidna on its next project? Nice. And thank you.
Check.
Check, check, check.
Okay. Cool. So I think I can start. Let me just set up the clock somewhere so I can control the time. All right. So today I'm gonna present how we can leverage storage proofs to build cool applications. Maybe a bit of intro before. This is me. I work on Herodotus. And yeah, that's it. So today we're gonna talk about storage proofs. I want to introduce this. Yes. I'm gonna present you storage proofs and explain why they're cool, how to work with them, why you need tooling to work with them, and yeah, a bunch of other things. Why is it even possible? All the complexities behind it, the trade-offs, and so on. So a few words about storage proofs. Why I really believe that they are cool, especially nowadays. So my thesis is that Ethereum is pretty sharded nowadays. And with storage proofs, we can essentially read the state in a almost synchronous manner, which is a pretty nice thing to do, given the circumstances. Yeah, and maybe also let me explain why is it even possible. So storage proof is essentially this idea that the entire state is committed in a cryptographic manner, using some data structure like Merkle trees, Merkle-Patricia trees, and so on. And yeah, we can essentially verify any specific piece of state at any point in time on any domain, which is pretty nice and doesn't introduce additional trust assumptions. We just rely on the security of like the base chain. So yeah, that's like storage proofs TLDR, why they're cool. Now a bit of like sponsored section. Sponsored section. So what we're doing at Herodotus. So our like goal is to make smart contracts self-aware in a way by providing access to historical state. We, like I said, my thesis is that Ethereum is pretty sharded nowadays. We want to unshard it by using storage proofs, and we want to enable synchronous data reads because today we do not have really nice ways to make synchronous data access without introducing new trust assumptions. So yeah, that's what we do. And how we achieve that? We achieve that by using obviously storage proofs. We use snarks, starks, and MPC. I will get why we even use all this tooling, but first a few words about storage proofs, what these are, and so on. It's so tricky, actually. I need to be multitasking. Okay, so what we're gonna cover in today's workshop. So all the basics required to like understand properly this primitive, how to like work with it, how you can generate these proofs, why they're pretty useful, and how actually you can access these commitments. I'll get later what we call a commitment in a trustless manner, and how we make smart contracts self-aware and enable historical data reads. Cool. So that's pretty tricky. So about the background that I want you to have for this workshop. So we're gonna like start from the biggest basics. So what is a hashing function? Just a very quick reminder. I hope it will take less than a minute. Like generalized blockchain anatomy, how an Ethereum header looks like, why Ethereum. We're not like pretty only like Ethereum focused. However, I think that for the sake of this workshop, it's the best to like present on this concrete example. Merkle trees, explain me like on 5. I will just quickly explain the idea, how it works, and what is a Merkle-Patricia tree without really going too much into the details. Yeah, finally, no, not finally, the anatomy of the Ethereum state. It's pretty important to like deal with this primitive, and finally how to deal with the storage layout. Cool. So hashing function. Essentially, it's this idea. Essentially, it's this idea that I can have a function that takes some input of any size, and it always return an output of a fixed size. And now what's also important, there is no input. There are no two inputs that will generate the same output, and you cannot reverse the hashing function. So it means that given the output, you don't know what is the input. And this is what we call like collision resistance. Pretty useful primitive like used in blockchains. And I think that's pretty much it. I assume that everyone is like familiar with it. Like, yeah. Okay, why is it important? So generalized blockchain anatomy. So why we call it a chain? Because we have a bunch of blocks bind together, like linked together, because each block contains the reference to the parent hash, and the previous header contains the reference to the parent hash, which is pretty cool. And let me remind what the hash, the parent hash or the block hash of on Ethereum is. It's essentially the hash of the header. Pretty important to deal with these primitives and make smart contracts self-aware, so accessing historical state. So just keep that in mind. Let's get to the next part. So, no. I think I'm missing one slide. No, it's the correct one. Okay, so this is an Ethereum block header. As I said, we're gonna go through the example of Ethereum concretely. So a bit of anatomy. So to access state, obviously we need the state root. What is the state root? Is the root of the Merkle-Patricia tree of the Ethereum state. We also have the transactions root, which is pretty useful if you want to access historical transactions like their entire body, and receipt root. So it's pretty useful to access any events, logs, and so on. And all of these are like root of the Merkle-Patricia tree. A Merkle-Patricia tree is a Merkle tree, just think of it in that way. And most importantly, we have the parent hash. And with the parent hash, we can, in a way, go backwards. I think that's it. Let's get to Merkle tree. So essentially, it's this idea that I can take whatever amount of data, and I can commit it in a cryptographic manner by using this data structure. So on the left side, we see a standard Merkle tree. So essentially, all the data goes to the bottom, and we essentially hash it. You know what the hashing function is, then we combine these two hashes together, we hash it, and we keep doing that till we get to essentially one hash, and this is what we call the root. Merkle-Patricia tree, modified Merkle-Patricia tree to be exact. This is the data structure that we use in Ethereum. What you see here, I hope you see, on the top we have the state root, and essentially the state root is the root of this tree. And now how it works and how you should think of this, it's a pretty complex data structure. I don't want you to bother with it today, but essentially we have three types of like nodes. We have leaf nodes, extension nodes, and branch nodes. So leaf nodes contain data, branch nodes contain data, and extension nodes, like on the high level, just help us to like sort of navigate in that tree. But to be honest, to deal with storage proofs, you don't really need to understand this part, but to like build on the low level as we do, obviously we need to deal pretty a lot with that part. Okay, so Ethereum state, how is it constructed? Most important takeaway, it's a two-level structure. So I mentioned that the state root is a commitment of the entire state, but it's not really true because Ethereum is does it still okay, works. It's account based, and essentially the state root is the commitment of all the accounts that exist on Ethereum. And what an account is made of, it's made of a balance, like the ETH balance. It's a nonce, transaction counter, storage root. The storage root is like the root of another Merkle-Patricia tree, and this Merkle-Patricia tree contains a key value database that holds like the mapping from storage key to its actual value. And finally, we have the code hash. It's essentially the hash of the bytecode. So main takeaway, first, we access accounts. And once we have the account storage root, we can access its storage. Okay, cool. So to sum it up, like the background, so main takeaways. Given the block state root, you can recreate any state for this specific block on this network. And given an initial trusted block hash, you can essentially recreate all the previous headers, which is pretty cool and important to get the ideas that I will explain like pretty soon. Okay, so as it's gonna be a workshop, it's a short one, so I won't let you code, but I will show you some concrete examples. So what I want you to like go through with me today is how we can prove the ownership of a lens profile on another chain. So a bit of background. Lens profiles are represented as NFTs, and Lens is deployed on Polygon. I think that's it. How do we get to this? So first of all, the question that we need to answer to ourselves is, how does Polygon commit to Ethereum L1? Because if we want to, like, let's say, prove the ownership of a lens profile on Optimism, we need to know the state root of Polygon. But there is Ethereum L1 in the middle, so how do we actually access this on Ethereum L1 primarily? So Polygon is a commit chain, and it commits to Ethereum a bunch of things every some amount of time. And essentially on L1, we do not validate the entire state transition, but we just verify the consensus of Polygon. And these checkpoints, how they call it, essentially contain state roots and so on. I mean, not directly, but we can access them. And let's get to this part. So this is taken from Polygon's documentation. And this is how a checkpoint looks like. So as you can see, the checkpoint is made of a proposer. So who proposed the block, start block, end block. Give me a second, I will get to this. And most importantly, we have the root hash. So the root hash is essentially a Merkle tree, not a Merkle-Patricia tree, that contains all the headers. And which headers? The headers in the range of start block and end block. Cool. So now, if we get back to the previous part, we can essentially prove with this commitment that we know the valid state root of Polygon, first given block. Okay, a bit of hands-on. So we want to prove that I own a lens profile on Polygon, whatever. So number one, we go to the contracts. We see a contract, we go through it, and we see that essentially there is a bunch of logic on top of this ERC 721. This is like the basic ERC 7.1. As you can see, it's an abstract contract, and it's slightly modified. Instead of having like a standard mapping from like token ID to its owner, we have like token ID to token data. Token data is a struct. This struct is 32 bytes in total. 20 bytes is the actual owner, and the remaining 12 bytes represent when the token was minted. Okay, but how do I actually prove it? Oh, and also, very important thing when dealing with storage layout, we have something that is called like slot indices. So each variable has a given slot, like in the some sort of meta layout. I call it like that. It's probably the right way. Anyways, this mapping has like the slot index 2. I will get to this part in a second, why it's 2. And we have a mapping from token ID. So uint to 32 bytes of data represented as a struct, but just think of it as some bytes. Okay, so I guess most of you use Hardhat. So I'm gonna present on Hardhat. There is a very, very cool tool to deal with storage layouts. It's called obviously Hardhat storage layout. This is how you install it. It's literally yarn install Hardhat storage layout. You add one comment to your Hardhat config. You write a new script that contains literally 8 lines of code. You run the script and you get this weird table. And what does it really tell you? And oh, and by the way, why this tool is pretty useful? As you see, this contract is abstract. So some other contracts does it still work? Yeah, some contracts can inherit from it, and obviously, while we inherit the storage layout, I mean, these indices can get more trickier because it also depends. Okay, so it's pretty hard to coordinate like one hand with another hand, even though I'm Italian. Okay, anyways, yeah, we know this slot in this index, and that's how we get it. We have a column that is called storage slot. And as you see, underscore token data is marked as 2, and that's it. Okay, but what do we do with it? How do we get this storage key? And yeah, that's it. Let me check the time. Okay, so a bit of hands-on. How do we get the actual storage? It sounds scary, and it's meant to be scary. So we know the slot index, the storage index. I want to prove that it's like 0x35 owns with ID 3594. How do we get the storage key? We essentially do this operation. So we concatenate the slot, the key in the mapping, which is 3594 because this is the token ID. As you know, we have a mapping from token ID to token data. Token data contains the Okay, so we concatenate this with the storage index. We hash it all together. This is the storage key that we have. If you're interested how to deal with it for like more complex mappings and like layouts, like the solidity documentation, it's explained pretty well. So now let's, to make sure we got the proper storage key, let's just check it. How we can check it? Super easy. Let's just make a one RPC call to get this storage at some specific key is the if get storage at. So the parameters. We want to access the storage of what? Of the lens hub. Lens hub is a contract that essentially is the representation of these profiles, and its address is 0xDDD4 and so on. And the slot. Oh, is it better? Oh, it's much better. And the slot, the storage key is 0x1, so essentially that's the hash that we got. And the result is 0x000, And we know that it's 32 bytes of data where we have 20 and 12. So let's split it into 12 and 20 bytes. And what we have is some number, like you can see 0x, a lot of zeros, then 62 till d. And this looks like a small number, so apparently it is a timestamp. And the second part is like 35, 57, and it's literally our address. So we got it correct. We have the proper storage key. Cool. But how do we actually get to storage proofs? So there are standardized methods in like the JSON RPC standard for Ethereum clients, and this method is called ETH get proof, which essentially given the contract address, so better call it account address in this specific case, allows us to generate a state proof. And the last argument, the second argument is an array that contains all the storage keys that we want to prove. There is another argument, which is 0x1a. It's essentially the block number for which we prove the state. Yeah, let's call this method. Oh, by the way, you might have a question, how do we deal with this method on non-EVM chains? Because, for example, on some specific rollups, this method is like not supported. Actually, it's not a big deal, because if you think of it, we just need the database, and on top of this database, we can literally build this method. We just need to know how the storage is constructed. Okay, this is the proof. It looks scary. It is scary. This entire object is 4 kilobytes of data. And now I mentioned before that the state is like a two-level structure. First, we have a proof for the account itself, and then we have the proof for the storage, for the actual storage slot. It is scary. It's meant to be scary. One proof is like more or less 600 bytes. 700 bytes, it really depends, like bigger the storage is, then bigger the proof is, and also more accounts we have, then bigger the account proof is. So that's a lot of cold data, if you can imagine. And yeah, that's pretty bad. Why? Because we need to post this proof on the chain, so it's a lot of cold data. But okay, let's try. What's gonna be the cost on like an EVM chain? That's the cost. It's like 600K of gas. That's a lot. That kills almost every single application that you want to build on top of this nice primitive. So it's pretty bad. And why is it that bad? So I explained on the high level what Merkle trees are and Merkle-Patricia trees are. On Ethereum, we use Merkle-Patricia trees. And essentially, there is a trade-off that when using Merkle-Patricia trees, the proof is slightly bigger. It's like harder to decode it because actually we need to do a bit of decoding there. But we need to do less hashing. So this is a trade-off. But depending where we actually verify this proof, it might be more feasible to verify like a proof that is based on Merkle-Patricia trees or Merkle trees. Okay, but there is a solution. And the solution is, what if we snarkify such a proof? And we verify this proof inside the snark. Why is it cool? Because we can, like, let's say that I'm gonna verify this proof inside a Graph 16 circuit. And yeah, the verification costs more or less like 210K gas. The proof is like way less than 600 bytes. So it's good. So essentially get rid of the cold data because the proof itself can be the private input to the circuit. Yeah, we can like use multiple proving system depending on the actual use case. And now, why is it like very, very cool? So first of all, it removes cold data. Second of all, it allows us to deal with very unfriendly hashing functions or the EVM. These the ones that we don't have precompiled for, like let's say Peterson. So it might be like super expensive to verify such a proof on the EVM because first of all, it's a lot of cold data and the hashing function is pretty like unfriendly. But what if we can like do it inside the snark and just verify a snark? And yeah, so another benefits, this really, really helps in abstracting the way how we verify these proofs because you don't need to have like one generalized verifier for each type of proof, but you can essentially abstract it behind the snark. Which is great. These numbers were taken from a very nice article written by A16Z, like a bunch of a few months ago. Yeah, and I think that's pretty much it. Let's get to the next slide. So synchronous cross-layer state access. So how can actually a contract deployed on some layer access the state of another L2 or L1? So I mentioned that we always need the state root, but because all of these systems have a native messaging system, we can send the small commitments, like for example, the block hash to like L1. Usually it goes all through L1. And yeah, we can like unroll it or send the state root directly. And also we don't need to rely on messaging, but we can, for example, rely on the fact that Polygon is like a commit chain, and all these rollups like commit from time to time. They're like batches and so on. So this is like pretty important, and we sort of can get the commitment from which we'll recreate the state directly on the one and then send it to another. So if let's say Polygon commits on L1, I can send this commitment then to Startnet, and Startnet do the actual verification. Cool. So now, how do we actually do that? So let's break the entire flow into like smallest pieces. So the flow is the following. We need to have access to the commitment, which is either a block hash or a state root. And again, we can get it either by sending a message, relying on the fact that is this chain commit. So in a sense, it's still a message. We can relate in an optimistic manner, or we can go even more crazy and verify the entire consensus. Okay, so this is step number one. We need to get the commitment. Step number two, we need to somehow access the state root, so the commitments of the state from like a previous block or the actual block, because keep in mind that these commitments are only block hashes. And with block hashes, we can recreate headers, but we cannot access the state. Okay, so once we have the state root, we obviously need to verify this state/storage proofs. Okay, and there are multiple approaches to do that. All of them come with some trade-offs, and let's go through all these approaches. So approach number one, messaging. So I can send a message from, let's say, Optimism to Ethereum L1. I can get the opcode. I can get the block hash by just calling the proper opcode, and I get it. It takes some time, but still I get it. This is approach number one. So we rely on the built-in messaging system, which is, I think, fair because the security of it is equal to the security of the rollup. And if you're deploying an application of this rollup, it's a fair assumption to do so. Yeah, it doesn't. Oh, now about the downsides. So the message must be delivered, so it introduces a significant delay, especially when dealing with the withdrawal period in the middle, and it requires interacting with multiple layers. So first you need to send a message, and then actually you need to consume it. So it's not ideal, but the trust assumptions are pretty okayish. Another approach, consensus validation. By the way, this like Gremlin is supposed to verify a bunch of BLS signatures. I hope it's self-explanatory. Okay, so maybe a bit of an intro. Right now we have POS as the native like consensus algorithm on Ethereum, which is pretty great because verifying the consensus is finally doable, because before like verifying the hashing function ETH hash, which was used for proof of work, was very memory intense. So not possible to do inside the snark on chain directly. So it was almost impossible to do so. So now we also have this fork trace rule called LMD goes, which is implementable, but doing all of this like directly is pretty expensive. So we need to ideally wrap inside the snark, but there is another downside. So a few words about the trust assumptions. You verify the consensus directly, so it's fine. Do you introduce any trust assumptions? Not really, but the biggest downside that generating the proof actually takes some time. So to be honest, this approach is feasible, but comparing to messaging, like quite often is like almost the same, and you pay a lot of improving time and requires like having more advanced infrastructure. Okay, last approach that we actually use is something that we call like an optimistic relayer based on MPC. MPC stands for multi-party computation. Maybe before I explain how it works. Let me explain the image. I hope it's self-explanatory. So it's an MPC protocol. We have multiple parties. These multiple parties attest something. Then we have an observer that can challenge it. And then we have finally the commitment given to a specific chain, in this case, Darknet, once everything is fine. How does it work? So we have a set of trusted relayers, validators, however, and they attest that a specific commitment is valid. So how does it work? If we want to get the commitment, aka the block hash of block number X on Starknet, then instead of sending a message that would be delayed with a slightly delayed, we can essentially make an off-chain call, just get the latest one and essentially relay this message directly to Starknet. But it comes with a few downsides, because while we introduce some trust assumptions, but still it's okay. Okay, how does it work? So it works in a way that we have a bunch of off-chain actors who essentially make these calls, and it works more or less like a multi-sig. But the reason why we have MPC is because more validators you have, then obviously more secure it is. But more validators you have in a standard multi-sig approach, you have more signatures. So more in a way decentralized it is, then it's more expensive to verify, because you need to verify multiple signatures and you need to post the signatures. It's a lot of cold data. Such approach is not feasible on chains where cold data is expensive. So L1, optimistic rollups, and yeah. Okay, so how does it work? What is the actually MPC part doing? The MPC part is very simple. It's essentially signing over a specific curve, some specific payload, and the payload is the commitment itself, and that's it. Okay, so this is how we actually attest, but now why this approach is called optimistic and why it's still secure. So first of all, we just posted something on the actual L2, and as you may know, we can send messages from L1 to L2. And such a message can contain the proper commitment. So essentially, even if the validator set will lie, L1 will never lie. So you can just challenge such a message. And now, to participate in verifying these validators, it's super easy, because it's literally 2 RPC calls. One call is going to check the actual commitment on the actual chain, and the other one checks what is the claimed commitment. If you disagree, you just send a message. It costs roughly 60K of gas, and that's it. Everyone can do that. And again, the fraud proving window is pretty short, because it's essentially how long it will take to generate the proof of consensus, if it's possible, or how long does it take to deliver the message. And what is pretty cool in this approach, it's not gas intensive, and we verify just one signature. So that's about this approach. Let's make a recap and let's identify the trade-offs. So we have 3 approaches. The first one is messaging. The second one is validating the consensus. And the third one is having this optimistic relayer. So I categorize it in 4 categories. The first one is latency. The second one is the gas cost. The third one is trust. And the last one is what is the off-chain computation overhead. Why do I even list it? Because if we do some sort of proving, then obviously it takes time, because we need to generate the proof. So messaging. In terms of latency, we are quite sad, because, well, the message needs to get delivered. So once the message gets delivered to some specific L2, L1 will be able to generate already new blocks. So we don't have access to the newest values. In terms of gas cost, it's not bad, but it's not perfect, because we need to interact with 2 chains at the same time. So first we need to send the message and consume it. In terms of trust, we are pretty happy, because we trust the rollup itself, and that's a fair assumption. Off-chain computation overhead, we're very happy, because there is no computation to do off-chain. Verifying the consensus. So in terms of latency, we are sad, because we need to generate the proof. That we've done it. It takes a bit of time. In terms of gas cost, we are, I would say, sad, because we need to verify the actual ZK proof, which is way more expensive than just consuming a message or verifying a signature. In terms of trust, we are happy, because we verify the consensus itself. And computation overhead, it's significant, right? Because we need to generate a proof. Final approach, this optimistic relayer. So in terms of latency, we're happy because we simply make a claim and we post it on the other chain. That's it. Gas cost, we're very happy because we just verify a signature. In terms of trust, well, we are not that happy, but also not that sad at the same time, because it still can be challenged in an optimistic manner using a fraud proof. Computation, off-chain computation overhead, we're pretty happy because we participate like an MPC protocol. So essentially the overhead comes mostly from communication, not computation itself. Cool. So this is part number one. These are the three approaches. Obviously, I'm not going to say which one is the best because all of them come with some trade-offs. Okay, accessing the headers. I hope it's self-explanatory because we literally unroll something from the trusted input. And the trusted input is, again, a block hash for a specific block X. And if you follow the initial slides, it's essentially each block, given a block hash, you can recreate the block header. And knowing the block header, we can access the parent hash. And by knowing the parent hash, you can recreate the previous block header. So essentially go till the genesis block. So given this very small input, we can essentially unroll the state or whatever was present on the chain from this block till the genesis block. Okay, so as I said, I'm going to explain everything on the example of Ethereum. And today, all the block headers together are like roughly 7 gigabytes of data. So it's quite a lot. But okay, this is how we actually do that. This is the high-level concept and what are the approaches. So the first one, we call it like on-chain accumulation. So essentially, we do this procedure, this computation directly on the chain. So we provide all these properly encoded block headers inside the call data and the block hash that we might receive as like the trusted input by sending a message, relaying it in an optimistic manner, or validating the consensus. And yeah, like recursively go through all these headers and verify them. But there are many, many downsides because first of all, it's very call data intensive. It's very computationally intensive. And now we can store all these headers on the actual chain, but you know, even storing on an L2, storing 7 gigabytes of data is still a significant cost because the state on an L2 is reflected as call data on L1. So it's still expensive either way. But the cool thing is that I have direct access to like state roots or anything that I want to access. Next approach is on-chain compression. So we can still use the same approach as previously. So literally unroll it and process these 7 gigabytes of data, but instead of like storing them, we can just update the Merkle tree. It's a nice approach, but comes again with a few downsides. It's very computationally intense because if we have like millions of headers, we need to perform millions of hashes on the chain. That's expensive, but at least we save on storing data. And also we need to update the Merkle tree, which is another cost. Last downside is that we need to index all the headers that have been processed. Why we need to index them? Because if I want to access a specific block header, I need to provide the Merkle path because as we update the Merkle tree and we just store a root in the contract itself, then I need to know the path, right? So I need to index the data and essentially once it's the moment that I want to access it, I need to provide the Merkle path. This approach is okay. It's, I wouldn't say way better than the previous one, but it's way cheaper. Last approach. So there is a very cool primitive called Merkle mountain ranges. Love it. And the idea is let's do the same that we do previously inside the snark. So we can provide this tremendous amount of data as a private input to the circuit and essentially do the same computation like unrolling inside the circuit itself. And now we have a public input, which is the block hash, so essentially the commitment from which we unroll it. So the trusted input, the public input can be literally asserted when we do the on-chain verification. And while we unroll it, we can accumulate inside the Merkle tree or a Merkle mountain range. Why a Merkle mountain range is cool? Because, well, let's imagine that you want to have like 7 gigabytes of data processing one snark. Like the proving time is going to be horrible. And why would you even like prove these commitments for like the entire history. Like, do you really need that? Probably not. So let's chunk it like into smaller pieces. And Merkle mountain ranges are a pretty cool primitive that allow to do this. To do this. To give you like a bit of intuition, how does it work? It's essentially, think of it as a tree of trees. Yeah, so once we do all this proving like off chain, we simply verify the proof on chain. As you know, like verifying the proof is way cheaper than doing this directly on the chain. And still, we just provide a Merkle path, and that's it. We essentially have access to any sort of data we want. Let's do a recap again. So approach number 1, on-chain accumulation, on-chain compression, off-chain compression. 3 categories: prover overhead, gas cost, storage cost. Actually, gas cost should be computational cost. Okay, so prover overhead. On-chain accumulation, do we prove anything? Well, not really. So we are happy. On-chain compression, well, we still like need to update the Merkle tree. I think actually there is an issue here, so I'll just skip this part. Off-chain compression, we're very, very sad because, well, we need to prove actually significant computation. So the proving time is significant. Okay, now in terms of gas cost, the third approach is horrible because it just costs a lot because we do the entire computation. On-chain compression, well, we're a bit happy because we just do a bit of computation, but still, it's a lot of cold data, a lot of computation, but at least not so much storage. Storage cost, gas cost in the second approach, well, we just verify a proof, so it's cool. Okay, storage cost for the first approach, well, 7 gigabytes of data. It is horrible, so we are very sad. On-chain compression, storage cost for on-chain compression, we just store a root of the Merkle tree, so we are happy. And in the second case, we're even more happy because we just essentially keep updating the tree, and we don't even need to post a lot of cold data because the cold data we post is literally just the proof. So we're very, very happy. But again, I don't want to say that one of these approaches is the best one, because as you see, there are trade-offs. And yeah, so this part is actually pretty easy. So as you know, as you might noticed, here I was explaining like the second step when it comes to dealing with storage proofs. And now there is the last part, which is essentially verifying the proof itself. So approach number 1 is verifying the proof directly on the chain. Approach number 2, let's verify the proof inside the snark and then verify the snark. Approach number 3, let's verify multiple proofs inside the snark and then verify the snark. We can aggregate multiple snarks together and so on, but obviously there are some trade-offs, especially when it comes to proving time. And yeah, so now, why the first approach is feasible on ZK rollups, for example, on Starknet cold data is very cheap, and what we want to avoid in this specific proofs is cold data. So this approach is, for example, feasible on Starknet, but for example, if you want to verify like a proof on Optimism where cold data is very expensive, you want to reduce it as much as possible. So for that reason, you might want to use a snark. And finally, if you have like many slots that you want to prove, why can't you just verify them inside one snark? You're gonna pay improver time, but you just present one proof at the end. So this approach is cheaper, is the cheapest one, but only if you have multiple actions to take. So there are trade-offs. So let's identify them. Categories: prover overhead, latency, verification cost. So verifying the proof directly, prover overhead doesn't exist. Latency doesn't exist because we don't need to prove anything. Verification cost, well, it is significant because we need to pass cold data and we need to do the actual computation. So like going through the entire path, and each step in the path is one hashing function. Oh, and also, let me get back to the previous slide. I forgot, this is very important. Why wrapping inside the snark is pretty important. If you're like dealing with a storage layout that is using a specific hashing function, let's say for example Peterson is not available like on the EVM. Like you just need to implement it. It's not a precompile, so it's gonna be costly. But if you do it inside the snark and Peterson is pretty snark friendly, then well, you just verify snark on the one and you abstract it, so it's gonna be way cheaper. But again, there are trade-offs. let me get back to this. So I went through the standard Merkle-Patricia tree, snarkified proof, proof overhead. It exists, so we are not super happy. Latency, we're also not happy because we actually need to spend time on proving this thing. Verification cost, we are happy because, well, we just verify a proof, so it's fine. And snarkifying multiple proofs, the prover overhead is still there, latency is still there, it's even bigger because it takes a bit longer in proving time. And verification cost, we are super happy because essentially we can mutualize the cost of verifying multiple proofs by just verifying one single snark proof. Okay, went through quite a lot of things. Let's put this all together. So let's imagine we have 3 chains and we want to have interoperability between them. So we have chain Z, chain X, and chain Y. So it all starts with a message, aka commitment. We send a message in order to get the commitment. So let's say that we send a message from chain Z to chain X, because on chain X we want to access the state of chain Z. So what do? Once we have the commitment, we literally recreate all the headers using one of the 3 approaches. And once we recreated the header is still the point for which I want to prove the storage, I just verify a proof. And again, for verifying a proof, there are multiple approaches. But now let's say that on chain Y, I want to access the state of chain Z. And there is no direct communication between chain Y and chain Z. So it must be routed through chain X. By the way, I'm like talking about this in a pretty abstract way. By chain X, I just mean Ethereum layer 1. Yeah, so from chain X, I'm just gonna send again the commitment about chain Z as a message, and then simply recreate all these headers. As you may notice, it's pretty redundant because we perform the same computation on 2 different chains, and we don't need to do that, especially if we use like the third approach, which is generating the proof on chain. But now there is another problem. How do you actually know what you should do? Like, you need to be somehow aware of what is happening. And for that reason, we introduce an API. We don't expect like developers to deal with all that complexities, choosing the right approach for the direct thing. Essentially, right now our APIs optimizes cost-wise. Soon we'll be able to optimize latency-wise. And yeah, and essentially that's it. That's about our API. I highly encourage you to check this out. And yeah, like a few final words about the API. It acts as a coordinator. It optimizes the costs. It optimizes the cost because we can batch multiple things. And once the job is done, you get a notification like via webhook, via an event, like whatever you want. So essentially, you don't need to be like an infrastructure maintainer, and you can just focus on essentially building on top of this primitive. And I think that's it. Questions? So the API essentially is a REST API for now. We also have a JSON interface. We have off-chain, on-chain entry points. So we can request the data like by making an off-chain call, like calling a REST API or like calling a JSON RPC method. Or if your smart contracts like wants to access this data, then you just emit an event. We're gonna catch the event, and later on, like after a bit of time, feed this the specific data inside the smart contract. So we have like a bunch of interfaces. And by the way, speaking of like the off-chain entry points, once the entire like work is done on our side, you can get a notification. It can be like a webhook. We can like send you a bit of information like using a WebSocket. It can be essentially whatever you want. Oh yeah, so that's actually a great question. So different chains use a different like storage, I would say, architecture. They might commit to a Merkle-Patricia tree, Merkle tree, maybe even Verkle tree. And obviously, like I said, having a generalized verifier is like pretty, it's not a clean approach. So we essentially abstract it by using a snark. And inside the snark itself, we just do the proper work, like we go through the tree, like through the elements of the proof, and then we can like use a specific hashing function. So for example, now Poseidon is pretty popular. I think that Scroll uses Poseidon, and also zk-sync uses Poseidon. On the EVM, like performing Poseidon will be pretty expensive. So for that reason, you cannot verify the proof directly. But what you can do the entire verification inside the snark, and then on the one, you don't really care what the snark is like doing. You just verify it. So that's how we actually deal with it. If we need to have it abstracted, we have it abstracted. If we don't, then we just don't. Oh yeah. Oh yeah, that's actually a good question, because I think I went super technical. So actually, what we do at Herodotus, every 2 weeks we have some internal hackathons, and right before the merge, we build a proof of concept that we called merge swap, and essentially we allowed anyone to dump their proof of work ETH on proof of stake. And the way how it works, we literally build a bridge on top of this technology, and the bridge works in a way that you can lock your ETH proof of work inside a smart contract on the ETH proof of work chain. You can prove that you've done it on Ethereum proof of stake. You can, once the proof is verified, you can mint the ERC20 token, and you can do whatever you want with this token. And then if you want to withdraw back to Ethereum proof of work, you just burn it. You prove the fact that you burned on the other side, and yeah, that's it. Also, in terms of other use cases, I think that cross-chain collateralization is pretty cool, because this is the place where you want to avoid latency as much as possible, and you want to be as synchronous as much as possible. And essentially, that's what we do here, because our latency comes only from the proving time. But again, using some optimistic approaches and so on, there are a lot of things we can do here. I hope it answers the question. Okay, I think that's it. I have like 3 minutes, so I guess we can wrap it up. And yeah, thanks.